Hello there, and welcome to Science for Sleep, where curiosity settles in, the pace slows down, and science becomes something gentle enough to listen to while the world grows quiet around you. Tonight, we're going to drift outward, far beyond the moon, far beyond the planets, and even beyond the distant edge of our solar system, towards something that has fascinated humans for as long as we have looked up at the night sky. We're going to think about the first journey to another star and why, according to the laws of physics as we understand them today, that first journey will almost certainly be a one-way trip. Take a moment to get comfortable as you listen. Let your shoulders relax a little. Let your breathing settle into its own rhythm. There's no rush here, and nothing you need to figure out or memorize. We're simply going to explore an idea together, slowly, step by step, the way you might walk along a quiet path in the evening, noticing things as they come into view. Before we go any farther, I'm curious about something. Where are you listening from tonight? Is it late evening or very early morning? Perhaps it's the middle of the night when everything outside is still, and the only sounds are the quiet ones you don't usually notice during the day. It's interesting to think that while you're here, listening in your own little corner of the world, there are people scattered across the planet hearing the same words at completely different hours, under different skies, each of us carried along by time in our own way. And if you find this journey soothing, or interesting, or simply a pleasant way to unwind at the end of a long day, I'd be grateful if you considered liking the video or subscribing to the channel. It helps this small, quiet space reach others who might need a calm moment too. But for now, there's nothing you need to do except listen. So let's begin with a simple thought. For thousands of years, the stars were lights in the sky, distant and unreachable, part of the scenery of the universe rather than destinations. People told stories about them, navigated by them, wondered about them, but the idea of actually travelling to one would have seemed no more practical than walking to the moon. The distances were simply too vast to imagine in any concrete way. Then, over the last few centuries, something changed. We began to measure the universe. We learned how far away things really are. We discovered that stars are not tiny points of light on a dome, but enormous suns, many of them larger than our own, scattered across distances so large that ordinary units stopped being useful. And gradually, a new question began to form, one that still captures the imagination today. Could we ever go there? Not just send signals or robotic probes, but actually go. Leave the solar system, cross the darkness between stars, arrive somewhere no human has ever been. It's a powerful idea, and it has inspired generations of scientists, engineers, and dreamers. But the more we understand the physics involved, the clearer something becomes. The first time humans make that journey, if it ever happens, the people who go will almost certainly know that they are not coming back. Now, that might sound a little dramatic at first, but the reasons behind it are not mysterious or speculative. They come directly from the basic laws that govern motion, energy, and time itself. These laws are not harsh or cruel. They're simply consistent. They describe how the universe behaves, whether we like the answers or not. To understand why a return trip is so difficult, it helps to begin with something very simple: distance. Imagine stepping outside on a clear night and looking up at the stars. The nearest one to Earth, other than the Sun, is Proxima Centauri. It's part of a small star system about 4.24 light-years away. That number is often quoted, but it's easy to say without really feeling what it means. A light-year is the distance light travels in 1 year. Light moves at about 300,000 kilometers per second. Every second it could circle the Earth more than 7 times. In a single minute it travels farther than any spacecraft humans have ever built could travel in years. And in 1 year, light covers about 9.46 trillion kilometers. So when we say Proxima Centauri is 4.24 light-years away, we mean that even light itself, the fastest thing in the universe, takes more than 4 years to get there. That's the nearest star. To put it another way, if you could travel at the speed of the fastest spacecraft ever launched, it would take tens of thousands of years to reach that distance. Not decades, not centuries, tens of thousands of years. Right away you begin to see the challenge. Interstellar space is not just far, it is so far that the scales involved stretch beyond ordinary intuition. Our everyday experiences with distance, walking across a room, driving across a city, even flying across an ocean, don't prepare us for distances measured in trillions of kilometers. Yet distance alone is only part of the story. Because once you begin to think about travelling those distances, another question naturally appears. How fast could you go? At first glance, the answer might seem straightforward. Build a powerful enough engine, accelerate long enough, and eventually you could reach extremely high speeds. After all, we've been increasing the speed of vehicles for centuries, from sailing ships to steam trains to jet aircraft to spacecraft. It's tempting to imagine that this trend could continue indefinitely. But physics sets a boundary here, one that cannot be crossed no matter how advanced our technology becomes. According to everything we know, nothing with mass can be accelerated to the speed of light. As you approach that speed, the energy required to accelerate further increases dramatically. Closer and closer to light speed, the energy required grows larger and larger, without limit. This isn't a technological problem, it's a fundamental feature of the universe. So even in the most optimistic scenarios, a human starship would be travelling at some fraction of the speed of light, not equal to it. Perhaps 10%, perhaps 20%, perhaps more in very advanced designs, but always less than the ultimate limit. Now, suppose you had such a ship. Suppose you could accelerate to a significant fraction of light speed and maintain that velocity for years. Even then, the journey to the nearest star would take decades from the perspective of people on Earth, and years or decades for those aboard the ship, depending on how fast they travelled. And then comes the crucial part that often receives less attention. If you want to return, you must slow down, turn around, and accelerate all over again. Every bit of speed you gain on the way out must be removed before you can stop at your destination, and every bit of speed you gain to head home must again be removed when you arrive back at Earth. Each of those steps requires enormous amounts of energy. So the journey is not just one long push forward. It's a sequence of accelerations and decelerations, each demanding fuel, power, and time. That leads to one of the central difficulties of interstellar travel, carrying what you need. Rockets work by throwing mass backward to push themselves forward. The faster you want to go, the more propellant you need. But the more propellant you carry, the heavier your spacecraft becomes, which means you need even more propellant to accelerate it. This cycle quickly becomes overwhelming. Engineers call this the tyranny of the rocket equation, and it is one of the most stubborn constraints in all of spaceflight. For journeys within the solar system, this challenge is difficult, but manageable. For journeys between stars, it becomes extreme. It's not impossible to imagine propulsion systems that don't rely entirely on onboard fuel. Concepts like light sails, nuclear propulsion, or beamed energy have been studied seriously. These ideas may allow spacecraft to reach very high speeds without carrying vast amounts of propellant. But even these approaches face a common issue. Leaving is easier than coming back. If a powerful laser or beam of energy pushes your ship away from Earth, that beam can't easily help you slow down at another star unless an equally powerful system already exists there. And of course, when humanity makes its first interstellar journey, there won't be any infrastructure waiting at the destination. There will be no fuel depots, no stations, no guiding lights, just a distant star and whatever planets or debris happen to orbit it. That means the first travellers will likely have to bring everything they need for the entire voyage, including the energy required to slow down, and that requirement alone may make a return trip impractical, at least for the earliest missions. But physics introduces another twist, one that makes the story even more interesting. Time itself behaves differently at high speeds. According to Einstein's theory of relativity, the faster you move, the more slowly time passes for you relative to someone who remains at rest. This effect, called time dilation, has been measured many times using precise clocks on airplanes, satellites, and high-speed particles in laboratories. It is not theoretical speculation. It is an observed fact of nature. For travellers moving at a significant fraction of the speed of light, time aboard the spacecraft would pass more slowly than on Earth. A journey that might take decades in Earth's frame of reference could feel shorter to the crew. At first, this sounds encouraging. Perhaps you might think this makes interstellar travel easier. In some ways it does, but it introduces a different kind of one-way aspect to the journey. Even if travellers could return physically, they would be returning to a world that had aged far more than they had. Friends, family, cultures, languages, even nations might have changed beyond recognition. The travellers would be stepping into a future in which everything familiar had drifted away. So the one-way nature of the journey is not only about fuel or distance, it is also about time and about the way human lives unfold within it. And there is yet another factor to consider, one that is less obvious but equally important. Space between the stars is not completely empty. It contains thin gas, stray atoms, and tiny grains of dust. At ordinary speeds, these particles pose little threat, but at a significant fraction of the speed of light, even a grain of dust carries enormous kinetic energy. Impacts that would be harmless at low speed become dangerous at high speed. Protecting a spacecraft from this environment over years or decades is a serious engineering challenge. Shielding adds mass. Mass increases energy requirements, and again, the problem loops back on itself. So when physicists and engineers talk seriously about the first human journey to another star, they often arrive at a similar conclusion. The first mission will not be designed as a round trip. It will be designed as a voyage outward, with the expectation that the people who go will build a new life at their destination, rather than returning to the place they left behind. And that idea changes the nature of the journey entirely. It is no longer a trip in the usual sense. It becomes something closer to migration, or even to the earliest human journeys across oceans and continents, when groups set out knowing they would probably never see their homeland again. There is something both sobering and quietly fascinating about that thought. The first humans to stand beneath the light of another star may do so knowing that the Earth they remember exists only in memory, separated from them not just by distance, but by time and by the immense energy required to cross the gulf between suns. Running the numbers begins with a name that astronomers mention often, yet that most of us rarely think about in any concrete way: Proxima Centauri. This small, faint red dwarf star orbits within the Alpha Centauri system, and at a distance of about 4.24 light-years, it is the closest known star to our own Sun. On a cosmic scale, that distance is considered nearby. In everyday terms, however, it is almost unimaginably far. It helps to slow down here and unpack what that number actually means, because the phrase light year can sound like a technical term that slips past the mind without leaving much of an impression. A light year is not a measure of time at all. It is a measure of distance, defined as how far light travels in 1 year. Light moves at about 299,792 kilometers per second. That number is so large that it's difficult to picture directly, so it can be useful to translate it into smaller steps. In 1 second, light could circle the Earth more than 7 times. In the time it takes to blink, a beam of light could travel from Warsaw to New York and back again several times. Over the course of a single minute, light travels nearly 18 million kilometers. Now imagine that speed continuing, not for minutes or hours, but for an entire year without slowing down even slightly. Multiply that speed by every second in every hour of every day, and you arrive at roughly 9.46 trillion kilometers. That is 1 light year. So when we say Proxima Centauri is 4.24 light years away, we are saying that light itself, moving as fast as anything in the universe can move, takes more than 4 years to make the journey. Another way to approach this is to compare that distance with the scale of our own solar system. Earth orbits the Sun at an average distance of about 150 million kilometers, That distance feels enormous when we think about spacecraft and planetary missions, yet the nearest star is about 40 trillion kilometres away, roughly 270,000 times farther than the Earth is from the Sun. If the distance between Earth and the Sun were shrunk to 1 metre, then the nearest star in that same scale model would still be about 270 kilometres away. You could imagine placing a small lamp in one city to represent the Sun, and then travelling hundreds of kilometres before placing another tiny lamp to represent Proxima Centauri. Everything in between would be almost entirely empty. That emptiness is part of what makes interstellar travel so challenging. Space within a solar system feels crowded by comparison. There are planets, moons, asteroids, comets, and dust, all orbiting within a region that, while vast by human standards, is small compared to the gaps between stars. Once you move beyond the outer boundary of the solar system, the distances between objects increase dramatically. A spacecraft leaving Earth would spend years just reaching the region where the Sun's influence begins to fade into the broader environment of interstellar space. And that would still be only the first tiny step on a journey to another star. At this point, it can be interesting to consider how long it would take to reach Proxima Centauri using speeds we are familiar with today. The fastest spacecraft ever built, NASA's Parker Solar Probe, reaches speeds of around 190 kilometers per second during parts of its orbit. That is astonishingly fast compared to anything on Earth, but even at that speed, a journey of 4.24 light-years would take more than 6,000 years. 6,000 years ago, human civilization looked very different. Agriculture was still developing in many regions. Writing systems were rare or non-existent. Entire cultures have risen and fallen in the time span that such a journey would require, and that estimate assumes travelling continuously at that top speed in a straight line, which is itself an optimistic assumption. Real missions involve acceleration, navigation, and many practical constraints that would likely lengthen the trip even further. Because of this, any realistic discussion of reaching another star involves travelling much faster than any spacecraft we have built so far. Scientists often talk about reaching perhaps 10% of the speed of light as a plausible long-term goal, using advanced propulsion methods that are still in the experimental or theoretical stage. 10% of the speed of light is about 30,000 kilometers per second. At that speed, the journey to Proxima Centauri would take about 40 to 50 years as measured from Earth. That is within the span of a human lifetime, at least in principle. Yet even this scenario, which sounds encouraging at first, comes with important complications. Reaching such a speed would require enormous amounts of energy, far beyond what we currently use for any spacecraft, and slowing down at the destination would require a similar amount of energy again. This is where distance begins to reveal its true significance. It is not just the time required to cross the gap that matters. It is the energy required to accelerate a spacecraft to the necessary speed and then reduce that speed again at the end of the journey. Energy requirements increase with the square of velocity, meaning that doubling your speed requires 4 times as much energy. Pushing a large spacecraft to a significant fraction of light speed would require energy comparable to the total output of large power plants running for years, possibly decades. So the distance to the nearest star is not merely a number. It is a direct measure of the scale of the engineering challenge involved. Every kilometre of that distance must be crossed by a physical object that must carry or receive the energy needed to keep moving. There is another way to appreciate these distances, one that astronomers sometimes use when teaching students about the structure of the galaxy. Imagine shrinking the Sun down to the size of a grain of sand. At that scale, Earth would be a microscopic speck orbiting just a few centimetres away. Jupiter might be several meters distant. The entire solar system would fit comfortably within a large room, but the nearest star at that same scale would be thousands of kilometers away. Not across the room, not across the city, but across continents. The galaxy, in this model, becomes so vast that individual stars are separated by distances that dwarf even planetary systems. This is why interstellar travel is fundamentally different from travelling within a solar system. The challenges are not just larger, they belong to a different category entirely. It is the difference between crossing a lake and crossing an ocean so wide that the far shore is beyond the horizon in every direction. As we think about this, it is worth remembering that distance also affects communication. Signals travel at the speed of light, which is the fastest speed available in the universe. If you were orbiting Proxima Centauri and sent a message back to Earth, it would take more than 4 years to arrive. A reply would take another 4 years to return. A simple conversation would stretch across nearly a decade. This delay would shape every aspect of an interstellar mission. Decisions would need to be made locally, without guidance from Earth. Emergencies could not be solved by asking for instructions. The travellers would, in a very real sense, be on their own. Distance, then, is not just a physical separation. It is also a separation in time, in communication, and in experience. The farther you go, the more disconnected you become from the place you left behind. There is something quietly humbling about realizing how small our solar system is compared to the spaces between stars. The planets that seem so distant to us are, in cosmic terms, neighbours sharing the same small neighbourhood around a single star. Beyond that neighbourhood lies a vast darkness, punctuated by distant points of light, each one separated from the next by distances that challenge both engineering and imagination. And yet, despite all of this, the idea of travelling to another star remains compelling. Perhaps it is because humans have always been drawn to horizons. When early sailors looked out across the ocean, they also faced distances that seemed impossible to cross with the technology of their time. When the first aircraft were built, crossing entire continents in hours would have sounded like fantasy. Still, there is an important difference. Oceans and continents are large, but they are finite in ways that interstellar space is not. The scale of the challenge here is measured not just in kilometres, but in fundamental limits imposed by physics itself. Understanding those limits requires looking more closely at the nature of speed and at the rule that governs all motion in the universe, the fact that nothing can travel faster than light. That rule, simple as it sounds, has profound consequences for any journey between stars, shaping not only how long such a trip would take, but why returning from it becomes so difficult in the first place. Thinking about the speed of light naturally leads to a deeper question, one that helps explain why distances between stars are expressed in light years in the first place. It is not only because the numbers become more manageable, though that is certainly part of it. The more important reason is that, in the universe, distance and time are closely connected. Light does not merely illuminate space, it also measures it. To see why this matters, it helps to begin with something familiar. Imagine you are standing far from a mountain range at sunset. The light you see reaching your eyes left those mountains a fraction of a second earlier. The view feels immediate, but even across a few kilometres, there is already a small delay between the moment light leaves an object and the moment you see it. Normally that delay is so tiny that we never notice it. Light is so fast that, on human scales, its travel time feels instantaneous. Flip a light switch, and the room brightens immediately. Look at a friend across the street, and you see them as they are, not as they were. But as distances grow larger, the delay becomes more noticeable. Light from the moon takes about 1.3 seconds to reach Earth. When astronauts walked on the lunar surface, every radio message and every television image was already more than a second old by the time it arrived. If you could stand on the moon and look back at Earth with your eyes alone, you would see the planet as it was just over a second ago. That delay grows as distances increase. Light from the sun takes about 8 minutes to reach us. The sunlight warming your face right now or lighting the sky outside began its journey 8 minutes earlier in the core of the sun, then travelled outward and crossed nearly 150 million kilometres of space before arriving here. This means that if the sun were to vanish, hypothetically speaking, we would not know about it for 8 minutes. The sky would look normal, the daylight would continue. Only after those 8 minutes had passed would the change become visible. At first, that idea can feel slightly strange. but it is simply a consequence of the fact that information cannot travel faster than light. Light carries images, heat, and signals. It is the messenger that connects distant parts of the universe. Now consider the stars. When you look at them on a clear night, you are not seeing them as they are in this instant. You're seeing them as they were years, decades, or even centuries ago, depending on how far away they are. The nearest stars appear to us as they were a few years in the past. More distant stars show us light that began its journey before many of the technologies we take for granted even existed. This is one of the reasons astronomers think in terms of light years. A light year is not just a convenient unit of distance. It is also a measure of how far back in time we are looking. That connection between distance and time becomes especially important when discussing travel between stars. If a star is 4 light years away, that means even a beam of light, moving at the fastest speed possible, requires 4 years to make the trip. Any spacecraft, no matter how advanced, would take longer unless it could approach the speed of light very closely. But the meaning of a light year goes deeper than that. It also reflects something fundamental about the structure of space itself. In everyday life, distance seems straightforward. You measure the length of a road or the height of a building, and those measurements feel absolute. A kilometre is a kilometre, no matter who measures it or how fast they are moving. In the realm of high speeds and large distances, however, things are not quite so simple. According to Einstein's theory of relativity, measurements of distance and time depend on the motion of the observer. Two people moving at different speeds may disagree about how long a journey takes or how far it is, yet both measurements can be correct within their own frames of reference. This does not mean that distance becomes meaningless. It means that distance and time are woven together into a single structure called spacetime. Instead of thinking of space and time as separate things, physics treats them as parts of a unified whole. A light year, in that sense, is not just a distance measured with a ruler, it is a distance defined by the motion of light through space-time, and light has a special role because its speed is the same for all observers, regardless of how fast they themselves are moving. This constancy of the speed of light is one of the most important discoveries in physics. It means that no matter how fast you travel, if you measure the speed of light, you will always get the same value. This is not intuitive. If you throw a ball forward while running, someone standing still will see the ball moving faster than you do. Speeds usually add together in that way. Light does not behave like that. Its speed remains fixed, and as a result, space and time adjust themselves to preserve that constancy. Distances can contract, and time intervals can change depending on motion. These effects are tiny at everyday speeds, but become significant as velocities approach the speed of light. All of this means that when we talk about interstellar distances, we are talking about distances embedded in a space-time framework where motion, time, and distance influence one another. Yet even without considering relativity, the sheer scale of a light year is enough to reshape our intuition. Consider a thought experiment. Imagine a spacecraft travelling at 1 kilometre per second, which is already faster than most aircraft. At that speed, travelling 1 light year would take nearly 300,000 years. Increase the speed tenfold and the journey still takes tens of thousands of years. Even at 100 kilometers per second, far beyond the speed of conventional spacecraft, the trip would last thousands of years. The only way to make interstellar travel feasible within a human lifetime is to reach speeds that are a significant fraction of the speed of light, and reaching those speeds requires confronting the enormous energy demands involved. Energy, after all, is closely tied to velocity. The faster you want to go, the more energy you must supply. And when velocities become very high, relativity tells us that the energy required increases more and more rapidly. Each additional increase in speed becomes harder than the last. This relationship between energy and speed is one of the reasons why the distances measured in light years matter so much. It is not merely that stars are far away, it is that the energy required to cross those distances at meaningful speeds becomes extraordinarily large. Another way to appreciate the scale of interstellar distances is to think in terms of communication. signals travelling at the speed of light would still take years to cross the gap between stars. If a spacecraft reached Proxima Centauri and sent a message home, the people who launched it might be several years older by the time the signal arrived. A reply would take the same amount of time to return. This delay shapes the nature of any interstellar mission. It means that such a mission cannot rely on real-time guidance from Earth. The crew, or the onboard systems, must be capable of making decisions independently. In effect, the farther you travel, the more isolated you become, not only physically but also in terms of information. Distance, then, is not just about kilometres or light years. It is about separation in time, separation in communication, and separation in experience. It is also about the distribution of matter in the universe. Stars are not evenly spaced in a neat grid. They are scattered through the galaxy with vast regions of empty space between them. Even in the relatively crowded neighbourhood of our galactic spiral arm, the typical distance between stars is measured in light years. That emptiness can be surprising. Science fiction often depicts space as busy, filled with ships and stations and activity. In reality, interstellar space is extraordinarily sparse. A spacecraft travelling between stars would spend most of its journey surrounded by darkness, with the nearest star appearing only as a bright point of light, gradually growing brighter over decades. Yet that emptiness does not mean the journey is easy. Even a few atoms per cubic centimetre, encountered at high speeds, can pose hazards. Tiny particles of dust become dangerous projectiles when relative velocities are measured in tens of thousands of kilometres per second. Protecting a spacecraft over such long distances requires careful design, and every protective layer adds mass, which in turn increases the energy required for acceleration. So distance influences nearly every aspect of interstellar travel: the time required, the energy needed, the difficulty of communication, and the engineering challenges of surviving the journey. It is also worth remembering that Proxima Centauri, close as it is on a cosmic scale, is only one of many stars. The Milky Way galaxy contains hundreds of billions of them, spread across a disk about 100,000 light-years in diameter. Light itself takes 100,000 years to cross from one side of the galaxy to the other. Seen from that perspective, even the nearest star is only the first step into a much larger universe, and yet the first step is often the hardest. Crossing a few light years may sound modest compared to the scale of the galaxy, but it represents a leap far beyond anything humanity has attempted before. It requires mastering propulsion methods capable of sustaining high velocities for years, designing life support systems that can operate reliably for decades, and planning missions in which the travellers may never return to the world they left behind. All of those challenges arise from one simple fact: the distances between stars are vast, and the speed of light, while extraordinarily fast, is still finite. That finite speed is what gives the light year its meaning. It is not just a unit of distance, but a reminder that the universe has limits built into it. Information cannot travel instantly. Motion requires energy. Time and distance are linked in ways that shape every journey across the cosmos. As we continue exploring this idea, another question naturally appears. If the speed of light defines the scale of distance and the limits of travel, why is that speed a limit at all? What is it about the laws of physics that prevents anything with mass from reaching or exceeding it? Understanding why nothing can travel faster than light begins with a realization that, at first, feels almost counterintuitive. The speed of light is not just a property of light itself, it is a property of the universe. It represents a fundamental limit built into the structure of spacetime, and everything that has mass must obey it. To see why this is so, it helps to step back and think about how motion works in everyday life. If you push a bicycle, it moves. If you push harder, it accelerates more. There is resistance from friction and air, but in principle, there is no strict speed limit imposed by the laws of classical physics. If you had a perfectly smooth surface and a powerful enough engine, you could keep increasing speed indefinitely. That is how motion was understood for centuries, especially in the framework of Newton's physics. In that picture of the universe, speeds simply add together. If you throw a ball forward while standing still, someone watching sees the speed of your throw. If you throw the same ball forward while riding in a moving train, someone standing beside the track sees the speed of the train plus the speed of the throw. Motion is relative, and speeds combine in a straightforward way. For a long time, scientists assumed light behaved in the same way. If you shone a beam of light while moving, it seemed natural to expect that someone observing from a different frame of reference would measure a different speed, just as with the ball. But experiments in the late 19th century revealed something strange. No matter how carefully scientists measured it, the speed of light always came out the same. It did not depend on the motion of the source or the observer. Whether measured on Earth or inferred from astronomical observations, light always appeared to travel at the same speed. This result was deeply puzzling. If speeds normally add together, why didn't the speed of a light change depending on how you measured it? The answer arrived in the early 20th century when Albert Einstein proposed a new way of thinking about space and time. Instead of assuming that time flows at the same rate for everyone and that distances are fixed, Einstein suggested that the speed of light is the constant, and space and time adjust themselves to preserve that constancy. This idea led to the theory of special relativity. One of its key conclusions is that measurements of time and distance depend on the motion of the observer. Clocks moving at high speed run more slowly relative to stationary clocks. Lengths measured in the direction of motion become shorter. These effects are tiny at everyday speeds but become significant as velocities approach the speed of light. At first, this may sound abstract, but it has been tested repeatedly. Highly precise clocks flown on aircraft or carried aboard satellites show measurable differences in time compared with clocks on the ground. Particles accelerated to near light speed in laboratories exhibit time dilation, and other relativistic effects exactly as predicted. These are not theoretical curiosities, they are observed features of reality. So where does the speed limit come from? It arises from the way energy and motion are related. In classical physics, the kinetic energy of an object increases with the square of its speed. If you double the speed, the energy increases by a factor of 4. This relationship works well at low speeds, but breaks down as velocities approach the speed of light. Relativity shows that as an object moves faster and faster, more and more energy is required to increase its speed further. The closer you get to the speed of light, the more dramatic this effect becomes. Each additional increment of speed requires a larger and larger amount of energy. To reach the speed of light itself would require an infinite amount of energy, which is not physically possible. This is why objects with mass cannot reach or exceed the speed of light. It is not that there is a barrier in space or some invisible wall. It is that the energy required to reach that speed grows without limit. Light, however, behaves differently because photons, the particles of light, have no rest mass. They do not need to be accelerated from rest in the same way that massive objects do. They always move at the speed of light in a vacuum. That speed is not just how fast they happen to travel, it is an intrinsic property of their existence. Another way to understand this limit is to think about how cause and effect work in the universe. The speed of light also represents the maximum speed at which information can travel. If signals could move faster than light, it would become possible, under certain conditions, for effects to occur before their causes, at least from some points of view. This would create contradictions in the sequence of events, undermining the logical structure of physics. Relativity preserves causality by ensuring that no signal or influence can propagate faster than light. Events remain ordered in a consistent way for all observers, even if they disagree about the timing of those events. It is worth pausing here to reflect on what this means for interstellar travel. The distances between stars are measured in light years precisely because light sets the pace at which anything can move or communicate. Even the most advanced spacecraft imaginable must travel slower than light, and that fact alone guarantees that journeys between stars will take years, decades, or longer. And as speeds increase, other challenges arise. the energy required to accelerate a spacecraft grows enormously. The stresses on materials increase. Even small particles in space become hazardous at high velocities because the energy of an impact depends on speed as well as mass. A tiny grain of dust striking a spacecraft at a significant fraction of light speed would release energy comparable to an explosive impact. So the speed limit imposed by relativity is not just an abstract principle. It has practical consequences that shape every aspect of planning an interstellar mission. Sometimes people ask whether it might be possible to circumvent this limit by bending space itself, rather than moving through it in the usual way. Concepts like warp drives and wormholes appear in theoretical physics and science fiction, and some of these ideas are explored mathematically. However, they require conditions that may not be physically achievable, such as forms of energy or matter that have never been observed in the required quantities. At present, there is no experimental evidence that faster-than-light travel is possible, and every confirmed observation supports the conclusion that the speed of light is a true limit. That does not mean interstellar travel is impossible. It means that such travel must take place within the constraints imposed by relativity. Spacecraft may one day reach a significant fraction of light speed, perhaps 10 or 20% or even more in advanced designs. But they will still require years to cross the distances between stars, and if a journey outward takes decades, a journey back would take decades more, requiring additional energy for acceleration and deceleration, as well as systems capable of sustaining life or function over extremely long periods. Each of these requirements compounds the difficulty. The more carefully you examine the physics, the clearer it becomes that the first missions to other stars will not resemble the voyages of ships that depart and return within a few months or years. They will be long, demanding undertakings in which distance, energy, and time combine in ways that make a return trip increasingly impractical. The speed of light, then, is not merely a number in an equation. It is a boundary that defines the scale of the universe and the tempo at which journeys can unfold. It shapes how we see the stars, how we measure distances, and how we imagine travelling among them. If we cannot travel faster than light, and if reaching another star requires travelling at a significant fraction of that speed, just how much energy would be needed to make such a journey possible in the first place? If a spacecraft cannot exceed that limit, then reaching another star within a reasonable time means travelling at a significant fraction of that speed. And the moment you begin to think about accelerating something to such enormous velocities, you run directly into one of the most unforgiving realities in physics: the energy required. It helps to start with something familiar. When a car accelerates on a highway, its engine converts chemical energy stored in fuel into motion. The faster the car goes, the more energy it must expend to overcome air resistance and increase its speed. Even doubling the speed requires far more than doubling the energy input. This is something drivers notice indirectly in fuel consumption. Cars burn much more fuel at high speeds than at moderate ones. Now imagine scaling that idea up, not to hundreds of kilometers per hour, but to tens of thousands of kilometers per second. The energy involved grows to levels that are difficult to grasp using everyday intuition. In physics, the energy of motion is called kinetic energy. At ordinary speeds, kinetic energy depends on mass and the square of velocity. That square is important. It means that if you double the speed, the energy required increases by a factor of 4. Triple the speed, and the energy increases 9-fold. This relationship already makes high-speed travel expensive in energy terms, but as speeds approach a significant fraction of the speed of light, relativity changes the picture further. The energy required does not merely increase with the square of velocity. It rises more steeply because time dilation and relativistic mass effects begin to play a role. Each additional increase in speed demands disproportionately more energy than the last. To appreciate what this means, consider a spacecraft with a mass of 1,000 tons. That might sound enormous, but for an interstellar mission carrying life support systems, shielding, supplies, and propulsion equipment, it is not unreasonable. Some concepts for large interstellar vessels are even heavier. Accelerating a mass like that to 10% of the speed of light would require an amount of energy comparable to the total annual electricity consumption of entire nations. And that is only for acceleration. If the spacecraft intends to slow down when it reaches its destination, it must expend a similar amount of energy again to reduce its velocity. And if there is any plan to return home, the entire process must be repeated. Accelerate for the journey back, then decelerate again upon arrival. 4 major phases of energy expenditure, each enormous in scale. At this point, another factor becomes clear. It is not enough to have access to large amounts of energy on Earth. That energy must somehow be carried or delivered to the spacecraft, and carrying energy usually means carrying fuel, which has mass. That mass must itself be accelerated, which requires more energy, which in turn requires more fuel, and so on. This compounding effect is one of the central challenges in rocketry. Engineers refer to it through an equation developed by Konstantin Tsiolkovsky, often called the rocket equation. The details of the equation are not necessary here, but its implication is simple and profound. As the speed required for a mission increases, the amount of propellant needed grows exponentially. For interstellar travel, this becomes extreme. A conventional rocket carrying all the fuel needed to accelerate to high fractions of the speed of light and then slow down again would need to be unimaginably large, most of its mass consisting of fuel rather than payload. This is why scientists and engineers explore alternative propulsion concepts, including nuclear fusion drives, antimatter engines, and systems that use external energy sources such as powerful lasers pushing light sails. These ideas aim to reduce the amount of fuel that must be carried on board, but each of them introduces its own technical challenges. Nuclear fusion, for example, releases far more energy per unit mass than chemical reactions, which is why it powers stars. If fusion could be harnessed efficiently in a spacecraft engine, it might provide the necessary thrust for interstellar travel. However, controlled fusion on Earth is still an active area of research, and building a compact, reliable fusion reactor suitable for a spacecraft remains a formidable engineering challenge. Antimatter offers even greater energy density. When matter and antimatter meet, they annihilate each other, converting nearly all their mass into energy, according to Einstein's famous equation, E equals mc squared. In principle, a small amount of antimatter could produce enormous amounts of energy. The difficulty is producing and storing antimatter in meaningful quantities. Current technology can create only tiny amounts at enormous cost, and storing antimatter safely requires complex magnetic confinement systems. At present, antimatter propulsion remains a theoretical possibility rather than a practical option. Light sails offer a different approach. Instead of carrying fuel, a spacecraft could be pushed by beams of light or laser energy from a distant source. Photons carry momentum, and when they reflect off a sail, they exert a tiny force. Over long periods, this force can gradually accelerate a spacecraft to high speeds. This method has the advantage of reducing the amount of mass that must be carried on board. However, it introduces another difficulty. Once the spacecraft leaves the region where the beam can reach it, acceleration stops. Slowing down at the destination becomes a separate problem, because there may be no infrastructure in place to provide a braking force. All of these considerations lead to a common realization. The challenge of interstellar travel is not simply about building a faster engine. It is about managing energy on a scale far beyond what current space missions require. Energy must be generated, stored, converted into motion, and in many cases dissipated as heat. Each step involves losses, and each loss must be accounted for. Heat in particular becomes an important factor, because spacecraft cannot easily radiate large amounts of heat in the vacuum of space. Cooling systems add mass and complexity, which again feeds back into the energy requirements. Another aspect that often receives less attention is the energy required to sustain life. A long-duration mission carrying human passengers would need to provide air, water, food, temperature control, and protection from radiation for years or decades. All of these systems consume energy continuously. Even if propulsion was solved, maintaining a stable environment over such long periods would be a major undertaking. And then there is shielding. At high speeds, interstellar dust and gas become hazardous, as mentioned earlier. Protecting a spacecraft requires layers of material or electromagnetic fields capable of absorbing or deflecting high-energy impacts. These protective systems add weight, and additional weight requires additional energy to accelerate. The interplay between mass and energy becomes relentless. Every kilogram added to the spacecraft increases the energy required for acceleration. Every system designed to solve one problem tends to create new requirements elsewhere. Because of this, many realistic proposals for the first interstellar missions assume relatively small payloads, possibly robotic probes rather than large crewed vessels. Smaller masses require less energy to accelerate, making high speeds more achievable. However, if the goal is to send humans, the scale increases dramatically. Human beings require life support systems, living space, redundancy for safety, and provisions for psychological well-being over long periods of isolation. These needs cannot easily be reduced to the scale of a robotic probe, so the energy requirements for interstellar travel are not simply large, they are intertwined with every other aspect of mission design, from propulsion and shielding to life support and communication. And there is one more consideration that brings us back to the idea of a one-way journey. If a spacecraft uses most of its available energy to accelerate and reach another star, there may be little or no capacity left for a return trip. Designing a mission to go outward and establish a permanent presence may be far more feasible than designing one that can come back. This is not because physics forbids a return entirely, but because the energy costs grow so large that each additional phase of acceleration and deceleration becomes increasingly impractical. So when scientists talk about the first human journey to another star being one way, they are not making a philosophical statement. They are describing the outcome of calculations based on energy, mass, and velocity. Calculations that follow directly from well-tested physical laws. Looking closely at the energy needed to cross the distance between stars naturally leads to the next piece of the puzzle, and it is one that engineers have been wrestling with since the earliest days of rocketry. Even if you had access to enormous amounts of energy, you still have to carry the means of releasing that energy in a way that produces thrust. And the moment you begin to think about carrying fuel, a quiet but very stubborn law of physics comes into play, one that shapes every rocket ever built. This law is usually summarized in what is called the rocket equation. The name sounds technical, but the idea behind it is simple enough to understand without any mathematics. A rocket moves forward by throwing mass backward. That mass is usually hot gas produced by burning fuel or by heating propellant in some other way. As the gas shoots out of the engine, the rocket gains speed in the opposite direction. At first glance, this seems straightforward. If you want more speed, you burn more fuel. But the difficulty appears when you consider that the fuel itself has mass, and that mass must also be accelerated along with the spacecraft. Imagine trying to run while carrying a backpack. If the backpack is light, it slows you down only a little. If it is heavy, you must work much harder to reach the same speed. Now imagine that inside the backpack there are smaller backpacks, and inside those even more. Every layer adds weight, and every bit of extra weight requires more effort to carry. Rockets face a similar situation. To accelerate, they must carry fuel. But carrying fuel increases the total mass, which means more fuel is required to accelerate that additional mass. And that additional fuel has mass of its own which must also be accelerated. This cycle quickly becomes overwhelming. Engineers describe this effect by talking about mass ratios, the ratio between the total mass of a rocket at launch and the mass of the rocket after its fuel is spent. For missions within the solar system, these ratios are already large. A typical chemical rocket might be more than 90% fuel at launch, with only a small fraction of its mass consisting of the actual payload. Even with that extreme ratio, the speeds achieved are only a tiny fraction of the speed of light. To understand why fuel becomes such a problem for interstellar travel, it helps to think about how speed builds up in stages. A rocket does not instantly reach its final velocity, it accelerates gradually, burning fuel continuously to increase its speed. The amount of fuel required depends not only on the desired speed, but also on the efficiency of the engine, measured by something called exhaust velocity, which describes how fast the propellant leaves the engine. Chemical rockets, the kind used to launch satellites and astronauts today, have relatively low exhaust velocities. They are powerful enough to escape Earth's gravity and travel between planets, but they are not efficient enough for interstellar journeys. Even if you filled an enormous spacecraft with chemical fuel, the rocket equation shows that you would still fall far short of the speeds required. That is why scientists consider other propulsion methods such as nuclear thermal rockets, nuclear fusion engines, or antimatter drives, which could in principle achieve much higher exhaust velocities. Higher exhaust velocity means that each kilogram of propellant provides more momentum, reducing the amount of fuel required for a given change in speed. Yet even with very efficient engines, the rocket equation remains unforgiving. To reach high fractions of the speed of light and then slow down again, the amount of propellant needed becomes enormous. In many theoretical designs, the mass of the fuel would exceed the mass of the payload by factors of hundreds or thousands. At some point, the spacecraft becomes almost entirely fuel, with only a tiny portion devoted to everything else, including structure, shielding, instruments, and possibly people. And that fuel must itself be contained in tanks, pumped through engines and managed safely over long periods, adding further mass and complexity. There is another subtle difficulty as well. Fuel is not only heavy, it is also finite. Once it is burned, it cannot be replaced. A spacecraft travelling to another star cannot refuel along the way, because there are no stations in interstellar space, no convenient reservoirs waiting between the stars. Everything needed for the journey must be carried from the beginning. This is very different from travel on Earth or even in orbit around Earth. Airplanes can land and refuel. Ships can resupply in ports. Even spacecraft in low Earth orbit can, in principle, be resupplied by cargo missions. Interstellar travel offers no such opportunities. This is one of the reasons why many serious proposals for interstellar propulsion focus on methods that do not require carrying all the fuel on board. Light sails, for example, rely on powerful lasers or beams of energy projected from afar. Because the energy source remains behind, the spacecraft itself can remain relatively light. But this approach introduces a new challenge. While it may help accelerate a spacecraft, it does not easily solve the problem of slowing down at the destination. Without a powerful beam waiting at the other end, the spacecraft would arrive at high speed and pass through the target star system in a matter of hours or days, far too quickly to explore or settle. Slowing down requires energy just as acceleration does, and that energy must come from somewhere. Another idea involves using the interstellar medium itself as a braking mechanism, perhaps by deploying large magnetic fields to interact with charged particles in space. This concept, sometimes called a magnetic sail, is still speculative, and the forces involved are extremely small, meaning that deceleration would take years or decades. All of these ideas reflect the same underlying truth. Changing the speed of a spacecraft, whether speeding up or slowing down, requires exchanging momentum with something else, whether that something is expelled propellant, a beam of light, or particles in space. There is no way around this requirement because it follows directly from the conservation of momentum, one of the most fundamental principles in physics. Momentum must be conserved. If a spacecraft gains momentum in one direction, something else must gain momentum in the opposite direction. Rockets achieve this by throwing mass backward. Light sails achieve it by reflecting photons. Magnetic sails attempt to use the particles of the interstellar medium, but in every case, there is a cost in energy, time, or both. As speeds increase, another factor becomes important: the kinetic energy of the spacecraft grows rapidly, and all of that energy must eventually be managed. If the spacecraft is to stop at its destination, the engines or braking systems must dissipate that energy safely. If it cannot, the spacecraft will simply continue moving, carried forward by its own inertia. In practical terms, this means that designing a mission to another star is not just about reaching high speed. It is about planning the entire sequence of acceleration, coasting and deceleration, each phase governed by the same relentless physics. The rocket equation does not care about intentions or ambitions. It does not bend for optimism or imagination. It simply describes how mass and velocity are related when propulsion depends on expelling reaction mass. And every calculation based on it leads to the same conclusion. Carrying enough fuel for a round trip to another star is extraordinarily difficult, perhaps prohibitively so for the first missions. This is why many scientists believe that the earliest interstellar voyages, if they occur, will be designed as one-way journeys. By eliminating the need to carry fuel for the return trip, the total mass can be reduced dramatically, making the mission more feasible. The travellers would still face immense challenges, of course. Life support, shielding and long-term reliability remain formidable problems. But the burden imposed by the rocket equation would at least be less severe. There is something quietly profound in this realization. The first humans to leave the solar system may do so not as explorers expecting to come home, but as pioneers setting out to begin new lives in distant systems, knowing that the physics of propulsion makes return unlikely. As the discussion of propulsion leads naturally into higher and higher velocities, the nature of motion itself begins to change in ways that are not obvious at everyday speeds. When engineers design aircraft or even interplanetary spacecraft, they can usually rely on the familiar rules of classical mechanics. Speed increases in proportion to thrust, energy rises with the square of velocity, and although the numbers may grow large, the relationships remain straightforward. But once a spacecraft begins to approach a significant fraction of the speed of light, a different set of rules becomes important, and those rules reshape the entire problem of acceleration. To understand why, it helps to think again about what speed really means. In everyday experience, speed feels like something simple. Walking is faster than standing still. Driving is faster than walking. A jet aircraft is faster than a car. Each step upward feels like a continuation of the same pattern. If you had a powerful enough engine and enough fuel, it might seem that you could keep increasing speed indefinitely. Relativity changes that expectation. It tells us that speed is not just a matter of adding more energy. Instead, the relationship between energy and velocity becomes increasingly steep as velocity rises. At low speeds, the familiar kinetic energy formula works well, and acceleration behaves much as we would expect. But as velocity climbs toward a significant fraction of the speed of light, the required energy begins to grow much faster than intuition suggests. One way to picture this is to imagine pushing a heavy object across a smooth floor. At first, each push makes it move faster quite easily, but now imagine that with each increase in speed, the floor becomes slightly stickier, resisting motion more strongly. The faster the object moves, the more effort is required to increase its speed further. Near the speed of light, it is as if the floor becomes infinitely resistant, so that no amount of pushing can make the object go faster than that ultimate limit. This resistance is not friction in the ordinary sense. It does not come from the environment. It comes from the structure of space-time itself, and from the way energy and momentum behave at high velocities. Physicists describe this effect using a quantity called the Lorentz factor, often represented by the Greek letter gamma. The details of the formula are not necessary here, but its behavior is important. At low speeds, gamma is very close to 1, which means relativistic effects are negligible. At 10% of the speed of light, gamma is still only slightly greater than 1, but as speed climbs to 50% of light speed, then 70%, then 90%, gamma rises more and more rapidly. What this means in practical terms is that each additional increment of speed costs far more energy than the previous one. Accelerating from 0 to 10% of light speed is enormously difficult, but accelerating from 90% to 95% would require even more energy than the entire earlier acceleration combined. This growing cost of acceleration has profound consequences for interstellar travel. It means that there is a point beyond which increasing speed becomes impractical, not because it is forbidden, but because the energy requirements become overwhelming. Even reaching 10 or 20% of the speed of light would already demand energy on a scale far beyond current human capabilities. Pushing beyond that into the realm of half the speed of light or more would require resources comparable to the total energy production of civilization over long periods. Another aspect of relativistic motion is that momentum increases along with energy. In classical physics, momentum is simply mass multiplied by velocity. In relativity, the situation is more complicated. As an object moves faster, its effective resistance to acceleration increases. It becomes harder and harder to change its velocity, even though its rest mass remains the same. This is sometimes described informally as the object's mass increasing with speed, although modern physics prefers to think of it in terms of energy and momentum rather than literal changes in mass. Either way, the effect is the same from the standpoint of propulsion. The faster you go, the harder it becomes to go faster still. For a spacecraft, this means that the engines must continue producing thrust over long periods, supplying ever greater amounts of energy for diminishing gains in speed. And every kilogram of fuel or propellant used to provide that thrust must itself be accelerated to the same velocity, multiplying the energy required. The situation becomes even more challenging when you remember that acceleration is only half the journey. If the spacecraft is to stop at its destination, it must reverse the entire process, shedding the enormous kinetic energy it has gained. All of that energy must go somewhere. It cannot simply disappear. Engines must convert it into exhaust, radiation, or some other form of energy that can be carried away. Managing such enormous energy flow safely over long periods is an engineering challenge of extraordinary difficulty. Relativistic speeds also introduce subtler effects that influence the design of a spacecraft. One of these is time dilation, which we will explore more carefully later. For now, it is enough to note that clocks aboard a fast-moving spacecraft would run more slowly relative to clocks on Earth. From the perspective of the crew, the journey might feel shorter than it appears to observers who remain behind. At first glance, this might seem like an advantage, and in some ways it is. Travellers could reach distant stars within their own lifetimes if their spacecraft moved fast enough, but time dilation does not reduce the energy required for acceleration. The engines must still provide the same enormous amounts of energy to reach those speeds. There is another consequence of relativistic motion that becomes increasingly important as speed rises. The kinetic energy of even tiny particles becomes significant. Interstellar space contains sparse gas and microscopic grains of dust. At low speeds, these particles pose little threat, but at velocities approaching a significant fraction of the speed of light, even a speck of dust can carry the energy of a small explosive when it strikes a spacecraft. Protecting against such impacts requires shielding, and shielding adds mass. Added mass increases the energy required for acceleration, which may require more fuel, which adds still more mass. Once again, the challenges reinforce one another. Radiation also becomes more intense at high speeds. Cosmic rays and other high-energy particles can penetrate materials and pose risks to both electronics and biological tissue. A spacecraft travelling for years or decades at relativistic speeds would need robust protection, further increasing its mass and the energy required to accelerate it. These considerations illustrate an important principle. Interstellar travel is not limited by a single obstacle, but by a network of interconnected constraints. Speed, energy, mass, shielding, and propulsion are all linked. Improving one aspect often makes another more difficult. Because of this, Many realistic proposals for interstellar missions focus on moderate relativistic speeds, perhaps 10 to 20% of the speed of light. At those velocities, travel times to the nearest stars would still be measured in decades, but the energy requirements, while enormous, might be within the reach of future technologies. Even at those speeds, however, the cost of acceleration remains immense. A spacecraft would need to accelerate for months or years, then coast for decades, and finally decelerate for another long period. Each phase demands careful planning and precise control of energy and momentum. There is also the question of reliability. Engines operating for such long durations must function flawlessly, because repair opportunities would be limited or non-existent. Systems must be designed to operate autonomously, adapting to changing conditions without guidance from Earth, since communication delays of several years would make real-time assistance impossible. And beyond the engineering challenges lies the human dimension, a journey lasting decades, perhaps spanning a large portion of a human lifetime, would require not only physical endurance but also psychological resilience. The crew would live knowing that the acceleration they feel at the beginning of the voyage is carrying them farther and farther from the world they know, and that turning back would require energy and time that may not be available. All of this brings us back to the central theme that has been unfolding gradually. The laws of physics do not forbid interstellar travel, but they impose constraints that shape how such travel must occur. Relativistic speeds are possible in principle, but achieving and managing them demands energy on a scale that makes round trips extraordinarily difficult. The faster a spacecraft travels, the more expensive each additional increase in speed becomes. The closer it approaches the speed of light, the steeper the energy curve rises. And because the journey must include both acceleration and deceleration, the total energy required grows to levels that may make a one-way mission far more practical than a return voyage. If travellers moving at relativistic speeds experience time differently from those who remain on Earth, what does that mean for the journey itself? How would time dilation shape the experience of those aboard the spacecraft, and why does it offer both a remarkable advantage and a subtle complication for interstellar travel? Imagine sitting inside a spacecraft that has been accelerating steadily for months. Outside the windows, the sun has long since faded into just another bright star, and the familiar constellations have begun to shift in subtle ways. The instruments on board show that the ship is now moving at a substantial fraction of the speed of light, faster than any human has ever travelled before. Nothing inside the cabin feels unusual. The air is calm, objects behave normally, and conversations unfold in the same measured rhythm as always. Yet, according to the physics that governs motion at these speeds, something remarkable is happening, something that cannot be felt directly, but can be measured with extraordinary precision. Time inside the spacecraft is passing more slowly than time for people who remain on Earth. This effect is known as time dilation, and it is one of the central predictions of Einstein's theory of special relativity. Unlike many ideas in physics that remain purely theoretical, time dilation has been tested and confirmed repeatedly. It is not speculation or interpretation. It is a measured property of reality. To understand why time changes for fast travellers, it helps to begin with a simple principle. One of the foundations of special relativity is that the laws of physics are the same for all observers moving at constant speeds, and that the speed of light in a vacuum is the same for everyone, regardless of how fast they themselves are moving. This second statement is the crucial one, because it forces space and time to behave in ways that are not obvious from everyday experience. Consider a thought experiment often used to illustrate this idea. Imagine a clock built from two mirrors facing each other, with a pulse of light bouncing back and forth between them. Each time the light reaches one mirror, the clock ticks. For someone standing still relative to this clock, the light travels straight up and down, and the time between ticks is determined by the distance between the mirrors and the speed of light. Now imagine that the same clock is placed aboard a spacecraft moving at high speed relative to an observer on Earth. To someone inside the spacecraft, The light still travels straight up and down between the mirrors, and the clock appears to tick normally. But to the observer on Earth, the situation looks different. Because the spacecraft is moving sideways, the light follows a diagonal path, travelling a longer distance between each reflection. The speed of light is the same in both cases. That is the rule relativity insists upon. If the light travels a longer path at the same speed, it must take more time to complete each tick. From the perspective of the observer on Earth, the clock aboard the spacecraft is running more slowly. This is the essence of time dilation. Moving clocks run slow relative to stationary ones, not because of any mechanical effect, but because time itself is part of the structure of spacetime and depends on motion. At everyday speeds, this effect is so small that it cannot be noticed without extremely precise instruments. A commercial airplane flying across the ocean experiences time dilation, but the difference amounts to only a few billionths of a second. Atomic clocks, however, are precise enough to measure such differences. Experiments have been conducted in which atomic clocks were flown around the world on aircraft and then compared with identical clocks that remained on the ground. The travelling clock showed exactly the time shifts predicted by relativity. Satellites in orbit provide an even clearer demonstration. The clocks on board GPS satellites experience both special relativistic time dilation due to their speed and gravitational time dilation due to being farther from Earth's gravitational field. Engineers must account for these effects when designing the system. If they did not, GPS measurements would drift by several kilometers each day. The fact that your phone can determine your position with such accuracy is a quiet, everyday confirmation that relativity is correct. Now consider what happens as speeds increase far beyond those of airplanes or satellites. At 10% of the speed of the light, time dilation is noticeable but modest. A journey that takes 10 years, according to clocks on Earth, might feel slightly shorter to travellers, perhaps 9.5 years. As speeds climb to 50% of the speed of light, the effect becomes more pronounced. At 90%, time aboard the spacecraft passes less than half as quickly as on Earth. At even higher speeds, the difference becomes dramatic. A traveller moving at 99% of the speed of light might experience only a few years while decades pass on Earth. From the traveller's perspective, the journey feels shorter, even though the distance crossed is the same. This leads to one of the most fascinating consequences of relativity. In principle, if a spacecraft could travel extremely close to the speed of light, its crew could reach distant stars within their own lifetimes, even if the journey spans centuries in the rest frame of Earth. Time dilation compresses the subjective duration of the trip for those aboard. At first glance, this seems like a solution to the challenge of interstellar travel. If travellers experience less time, perhaps long journeys become more practical. But the situation is more complex than it appears. Time dilation reduces the duration of the journey as experienced by the travellers, but it does not reduce the energy required to achieve the necessary speeds. The engines must still supply enormous amounts of energy to accelerate the spacecraft. The constraints imposed by the rocket equation and the growing cost of acceleration remain unchanged. There is also another consequence that is less obvious but equally important. Time dilation is symmetrical for observers in different frames of reference, as long as they remain in uniform motion. The asymmetry appears when one of them accelerates and changes direction. In the context of interstellar travel, this becomes relevant when considering a return trip. Imagine two identical twins. One remains on Earth while the other boards a spacecraft and travels at high speed to a distant star and then returns. When the travelling twin comes back, they are younger than the twin who stayed behind. This scenario, often called the twin paradox, is not a paradox in the sense of being contradictory. It is a direct consequence of the different paths through space-time taken by the two individuals. For interstellar travel, this means that even if a return journey were technically possible, the travellers would come back to a world that has aged far more than they have. Friends, family and familiar surroundings might no longer exist. Languages could change, societies could transform, and the travellers might feel like visitors from another era. This aspect of time dilation contributes to the idea that the first journeys to other stars may effectively be one way, not only because of fuel and energy constraints, but also because of the passage of time itself. There is another effect associated with relativistic speeds that influences how travellers would perceive the universe. As velocity increases, the light from stars ahead of the spacecraft becomes concentrated and shifted toward higher frequencies, while the light from stars behind becomes stretched and dimmer. This phenomenon, known as relativistic aberration and Doppler shifting, would cause the sky ahead to appear brighter and more compressed, while the sky behind would fade. The cosmic microwave background radiation, normally invisible to human senses, would shift toward visible wavelengths at sufficiently high speeds, creating a faint glow in the direction of travel. These visual changes would remind the crew constantly that they are moving through space-time at extraordinary velocities. Despite these dramatic effects, life inside the spacecraft would feel normal. Biological processes would proceed at their usual pace. Conversations would take place in real time. Meals would be eaten, sleep would come and go, and daily routines would unfold much as they do on Earth. Time dilation does not feel like anything from the inside. It is only when comparing clocks in different frames of reference that the difference becomes apparent. This highlights an important point about relativity. It does not distort time in the sense of stretching or compressing it within one's own experience. Instead, it changes how different observers relate their measurements of time and distance to one another. Each observer experiences their own time as normal, while seeing others as running differently. For mission planners, time dilation introduces both opportunities and challenges. On one hand, it allows travellers to reach distant destinations within their own lifetimes, if sufficiently high speeds can be achieved. On the other hand, it complicates communication and synchronization with Earth. Messages sent between the spacecraft and Earth would not only be delayed by the finite speed of light, but also affected by the differing rates at which time passes in each frame. Navigating these differences would require careful calculations and precise timing systems, ensuring that trajectories and communication schedules remain accurate over years or decades. There is also a psychological dimension to consider. Knowing that time on Earth is passing more quickly than time aboard the spacecraft could shape how travellers think about their journey. Every year they experience might correspond to several years passing for those they left behind. The sense of separation would grow not only in distance but also in time. Yet, for those making the journey, time dilation could also bring a certain kind of reassurance. The vast distances between stars would not feel as overwhelming when measured by their own clocks. The journey, though long, would remain within the span of human experience. As these ideas come together, it becomes clear that time dilation is neither a simple advantage nor a simple obstacle. It is a feature of the universe that reshapes how journeys unfold, altering the relationship between travellers and the world they leave behind. And once the role of time itself is understood, another question naturally arises. If time dilation can shorten the perceived duration of a journey for those aboard a fast-moving spacecraft, why does it not solve the deeper problem of returning home? And why does the physics of long-distance travel still point toward the likelihood that the first voyages between stars will be one way? At first, the idea of time dilation can feel like a quiet kind of loophole, almost as if the universe has left a small door open for travellers willing to move fast enough. If a crew could accelerate to very high speeds and experience only a few years while decades passed on Earth, then long interstellar voyages might seem far less intimidating. From the perspective of the travellers, the distance would feel compressed in time, and the journey could fit comfortably within a human lifetime. Because of this, it is sometimes tempting to imagine that time dilation makes interstellar travel easier in a general sense, perhaps even allowing journeys to distant stars and back without too much difficulty. But when the details are examined carefully, it becomes clear that time dilation does not remove the most difficult parts of the problem. The obstacles that make a return trip so challenging remain in place, and in some ways they become even more pronounced. The first point to understand is that time dilation changes the passage of time experienced by the travellers, but it does not change the distance between stars in any absolute way. From the perspective of the spacecraft, distances in the direction of motion do contract, an effect known as length contraction. This means that the crew might measure the distance to their destination as shorter than observers on Earth would measure it. In that sense, the universe ahead of them appears compressed. However, this does not reduce the amount of energy required to accelerate the spacecraft. The engines must still provide the enormous kinetic energy needed to reach relativistic speeds. The fuel must still be carried or supplied. The shielding must still protect the ship from radiation and dust. All of the engineering challenges remain essentially unchanged. Time dilation, in other words, helps with the subjective experience of the journey, but does not reduce the physical work required to perform it. The second point is that time dilation works equally in both directions of travel. If a spacecraft accelerates away from Earth at high speed, time aboard the ship runs more slowly relative to Earth. But if the spacecraft later turns around and accelerates back, the same relativistic effects apply during the return leg. The total energy required to reverse course and accelerate again is just as large as the energy required for the outward journey. This is where the problem of fuel and propulsion reappears. A return trip requires not only reaching high speed, but also slowing down, turning around, accelerating again, and finally decelerating once more upon arrival. Each of these phases demands enormous energy, and carrying enough fuel to perform all of them becomes extraordinarily difficult. Even if propulsion systems far more efficient than today's rockets were developed, the energy requirements would still be immense. Time dilation does not reduce those requirements, because energy depends on velocity relative to the frame in which the acceleration occurs, not on how the travellers perceive the passage of time. There is also another subtle effect to consider. From the perspective of the travellers, the time required to reach a distant star may be shortened, but the time required for Earth to complete its own history continues as usual. When the travellers return, they would find that far more time has passed on Earth than they themselves experienced. This means that a round trip, even if technically feasible, would carry a profound cost in terms of separation from the society that launched the mission. The travellers might come home to a world that is centuries older, with cultures, technologies, and perhaps even languages that have changed beyond recognition. In that sense, time dilation does not merely fail to solve the return problem. It introduces a different kind of one-way aspect to the journey. Even if the spacecraft physically returns, the travellers themselves cannot return to the same time they left behind. Another factor that limits the usefulness of time dilation is the difficulty of achieving the speeds at which its effects become dramatic. At 10% of the speed of light, time dilation is noticeable but modest. Only as speeds approach a significant fraction of light speed does the effect become large enough to shorten journeys dramatically from the traveller's perspective. Reaching such speeds requires enormous energy, as discussed earlier. The closer a spacecraft comes to the speed of light, the more rapidly the required energy increases. Each additional increment of speed demands disproportionately greater effort. This steep cost makes it unlikely that the first interstellar missions will travel fast enough for time dilation to reduce travel times to only a few years. Instead, early missions may operate at more moderate relativistic speeds, perhaps 10 or 20% of the speed of light. At those velocities, time dilation shortens the subjective duration of the journey somewhat, but not enough to transform a decades-long trip into a short one. There is also the question of deceleration at the destination. Time dilation does not help with this problem. A spacecraft approaching another star at high speed must shed its kinetic energy to enter orbit or land on a planet. That energy must be dissipated through engines, sails, or other braking mechanisms. The process takes time, fuel, and careful planning, regardless of how time passes aboard the ship. If the spacecraft lacks the means to decelerate effectively, it will simply pass through the star system and continue into interstellar space. In that case, the journey becomes one way in the most literal sense, not because of time dilation, but because of the difficulty of stopping. Communication delays also remain unchanged. Signals cannot travel faster than light. So even if travelers experience only a few years during their journey, messages between the spacecraft and Earth would still take years to cross the distance. Coordination of a return mission would be complicated by these delays, especially if unexpected problems arose. Another practical consideration is reliability. A spacecraft designed for a round trip would need to function flawlessly for an extremely long period, possibly many decades or more. Systems would have to remain operational throughout the outward journey, the time spent at the destination, and the entire return voyage. The longer a mission lasts, the greater the risk of mechanical failures, radiation damage, or other unforeseen difficulties. Designing a mission that lasts a few decades is already challenging. Designing one that lasts twice as long, with all systems remaining reliable, becomes significantly more difficult. Time dilation does not reduce this requirement, because the systems must still operate for the full duration measured in their own frame of reference. There is also the human dimension. Even if time dilation allows travelers to experience a shorter subjective journey, they would still spend many years confined within a spacecraft, far from Earth, living in an environment that must be carefully controlled and maintained. The psychological and social challenges of such a mission would be considerable, and extending the mission to include a return trip would lengthen those challenges further. All of these factors combine to explain why time dilation, remarkable as it is, does not solve the fundamental difficulties of returning from another star. The physics of energy, propulsion, and reliability remain unchanged. The separation in time between travelers and those who remain behind becomes greater, not smaller. And the engineering challenges of deceleration and turnaround remain formidable. Time dilation offers a way to make long journeys more manageable from the traveller's perspective, but it does not remove the physical constraints that shape those journeys. It is a feature of relativity that changes how time is experienced, not a shortcut that eliminates the need for energy, fuel, and careful planning. Even if a spacecraft can reach another star within a human lifetime, what happens when the journey takes longer than a single lifetime? How would missions be planned if the travelers who depart are not the same people who arrive? And what would it mean for entire generations to live and die aboard a ship travelling between the stars? Long before a spacecraft ever approaches another star, it must pass through a region that, at first glance, seems almost perfectly empty. When we look up at the night sky, the darkness between stars appears calm and still, a vast silence with nothing in it at all. It is natural to imagine that once a ship leaves the solar system, it would simply glide through an endless vacuum, encountering nothing along the way. But the reality is more complicated, and at high speeds, even the faintest traces of matter in interstellar space become significant. Interstellar space is often described as a vacuum, and compared to the atmosphere of Earth, it certainly is. The density of matter between stars is extremely low. In some regions, there may be only a few atoms in each cubic centimetre. That sounds like almost nothing, and in many ways it is. Yet when a spacecraft moves through this environment at tens of thousands of kilometres per second, or even faster, those few atoms and tiny grains of dust begin to matter a great deal. To understand why, it helps to think about energy in terms of motion. The energy of an impact depends not only on the mass of an object but also on its velocity. At everyday speeds, small particles rarely cause serious damage. A grain of sand drifting in the air might bounce harmlessly off a surface, but increase the speed enough, and the same grain can become destructive. On Earth, this effect is familiar in a limited way. A small pebble thrown by hand is harmless, but the same pebble striking a windshield at highway speed can cause significant damage. The pebble itself has not changed, only the speed has. Now imagine that instead of highway speeds, the relative velocity is a significant fraction of the speed of light. At those velocities, even a microscopic particle carries enormous kinetic energy. A speck of dust striking a spacecraft could release energy comparable to a small explosive. The faster the spacecraft travels, the more dangerous these impacts become. Interstellar dust grains are typically tiny, often no larger than smoke particles. Yet at relativistic speeds, their energy increases dramatically. A spacecraft travelling at 20% of the speed of light would encounter interstellar particles with energies far beyond what ordinary materials are designed to withstand repeatedly over long periods. Protecting against this hazard is one of the major engineering challenges of interstellar travel. Shielding must be thick or sophisticated enough to absorb or deflect these impacts without allowing damage to critical systems. But shielding adds mass. An added mass increases the energy required for acceleration, which in turn increases the amount of fuel or propulsion needed. Once again, the challenges of interstellar travel are tightly interconnected. Some proposed designs suggest placing a sacrificial shield at the front of a spacecraft, a thick layer of material intended to absorb impacts gradually over the course of the journey. Others consider using electromagnetic fields to deflect charged particles before they reach the hull. Each method has advantages and limitations, and none eliminates the problem entirely. Dust is not the only concern. Interstellar space also contains radiation, and at high speeds, radiation becomes more intense in ways that are not immediately obvious. Cosmic rays, which are high-energy particles originating from distant stars, supernovae, and other energetic processes, constantly pass through the galaxy. On Earth, we are largely protected from these particles by our atmosphere and magnetic field. In deep space, that protection disappears. Astronauts aboard the International Space Station already receive higher doses of radiation than people on the surface of Earth, even though they remain within the protective influence of Earth's magnetic field. A spacecraft travelling between stars would be exposed to cosmic radiation continuously for years or decades. At relativistic speeds, another effect appears. Because of the motion of the spacecraft, particles and radiation in the direction of travel become concentrated and shifted to higher energies. This is related to the Doppler effect, the same principle that causes the pitch of a siren to change as an ambulance passes by. In the case of light and radiation, motion compresses wavelengths, increasing their energy. For a spacecraft moving at a significant fraction of the speed of light, radiation ahead of the ship becomes more energetic and more intense. Particles that would normally be relatively harmless can become penetrating and dangerous. This means that shielding must protect not only against physical impacts, but also against high-energy radiation capable of damaging electronics and living tissue. Radiation has cumulative effects. Over long periods, exposure can increase the risk of cancer, damage the nervous system, and degrade materials. Electronics can suffer from single-event upsets, in which high-energy particles alter the state of memory or disrupt circuits. Designing systems that can operate reliably under such conditions requires redundancy, error correction, and careful selection of materials. All of these protective measures add complexity and mass, reinforcing the recurring theme that every solution introduces new constraints. Another factor that becomes important over long journeys is erosion. Even if individual impacts are small, billions of them over years or decades can gradually wear away surfaces. This is similar, in a distant way, to how wind and sand shape rocks in deserts over long periods. For a spacecraft travelling at high speed, the process would occur far more rapidly. Engineers must consider how materials behave under continuous bombardment by high-energy particles. Protective layers might need to be replaced or designed to last for the entire duration of the mission, which could be measured in decades. The reliability of shielding becomes as critical as the reliability of engines or life support systems. It is interesting to note that interstellar space is not uniform. Some regions contain slightly higher concentrations of gas and dust, especially near nebulae or within certain parts of the galaxy. Navigating a spacecraft along a path that minimises exposure to denser regions might become an important aspect of mission planning. Mapping the interstellar medium in detail would therefore be an essential step before sending human travellers. Astronomers already study the distribution of gas and dust using telescopes that detect radio waves, infrared radiation, and other wavelengths. These observations provide a kind of weather map of interstellar space, showing regions of relative emptiness and regions where matter is more concentrated. Even in the emptiest regions, however, the hazards cannot be eliminated entirely. At high speeds, a spacecraft cannot simply steer around every particle. The sheer number of microscopic impacts over the course of years makes some level of shielding unavoidable. There is also a thermal aspect to consider. When high-speed particles strike a surface, their kinetic energy is converted into heat. Over time, this heating effect must be managed to prevent damage to the spacecraft. Radiators and heat dissipation systems become essential, and once again, these systems add mass and complexity. Despite all of these challenges, the environment of interstellar space is not hostile in the way that planetary surfaces can be. There are no storms, no atmospheric pressure, no gravity wells to escape. Once a spacecraft reaches its cruising speed, it can coast for long periods with minimal propulsion. In that sense, the emptiness of interstellar space is both a challenge and an advantage. There is little to slow a spacecraft down, but there is also little to protect it. The realization that interstellar space is not completely empty changes how we think about long voyages. The journey is not merely a matter of travelling from one point to another across a featureless void. It is a continuous interaction with a sparse but real environment, one that must be accounted for in every aspect of design. For robotic probes, these hazards are significant but manageable, especially if the spacecraft is small and travels at moderate speeds. For human missions, the stakes are higher. Lives depend on the integrity of shielding, the reliability of systems, and the ability to withstand years of exposure to radiation and impacts. All of this reinforces a broader conclusion that has been emerging gradually. Interstellar travel is not prevented by a single insurmountable barrier. Instead, it is shaped by many constraints, each of which adds weight, energy requirements, and complexity. The more carefully one examines the details, the clearer it becomes that designing a mission capable of going out and then returning is far more difficult than designing one that goes outward alone. Consider what happens to any object moving quickly through an environment, even one that seems almost empty. On Earth, we are used to thinking about heat and friction in terms of air resistance. Rub your hands together and they grow warm. A meteor entering the atmosphere glows and burns because of the enormous friction between its surface and the air. A spacecraft returning to Earth must endure temperatures hot enough to melt metal, unless it's protected by carefully designed heat shields. These are familiar examples, and they all have one thing in common. They involve motion through a relatively dense gas. Interstellar space is vastly thinner than any atmosphere, so at first it might seem that friction and heating would not matter there. Yet when velocities become extremely high, the situation changes in a subtle but important way. Even very small numbers of particles can produce measurable effects when the relative speed between those particles and a spacecraft is large enough. What matters is not only how many particles there are, but how much energy each collision carries. A useful way to think about this is to imagine driving a car in a gentle rainstorm. At low speed, raindrops strike the windshield lightly, barely noticeable. Increase the speed, and the impacts become more pronounced. At very high speed, each droplet strikes with surprising force. The number of droplets has not changed, but the energy of each impact has increased because energy depends strongly on velocity. Now extend that idea to the scale of interstellar travel. A spacecraft moving at a significant fraction of the speed of light would encounter individual atoms and tiny dust particles with enormous relative velocities. Each collision would release energy, and that energy would appear as heat or radiation at the point of impact. Over the course of years or decades, billions upon billions of such impacts would occur. Even if each individual event was small, the cumulative effect could be substantial. The outer surfaces of a starship would slowly absorb energy, and that energy would have to be managed somehow. Without adequate protection and cooling, temperatures could rise to levels that damage materials or disrupt delicate instruments. This brings us to one of the less obvious challenges of high-speed space travel: managing heat in a vacuum. On Earth, heat is easily removed by convection, the process by which warm air rises and cooler air replaces it. Fans, breezes, and flowing liquids all help carry heat away from objects. In space, convection does not occur because there is no surrounding fluid to carry heat away. Instead, spacecraft must rely on radiation to shed excess heat. Heat radiates away in the form of infrared light, a process that is much slower than convection. Radiators must have large surface areas to be effective, and those surfaces must be oriented so that they can emit heat efficiently into space. For a spacecraft travelling at high speed through interstellar space, this becomes a delicate balance. The ship must absorb energy from impacts and radiation, while also generating heat internally from its own power systems, life support equipment, and engines. All of that heat must be radiated away to prevent gradual overheating. Radiators, however, add mass and complexity. They must be protected from impacts, yet they must also be exposed enough to radiate heat effectively. Designing structures that can perform both functions is not simple, especially over the timescales required for interstellar journeys. Another factor to consider is the way materials behave under continuous exposure to energetic particles. When atoms in a solid are struck repeatedly by high-speed particles, their crystal structures can be damaged. Over time, materials can become brittle or weakened, a process known as radiation damage. This effect is well known in nuclear reactors and in spacecraft electronics, where radiation gradually alters the properties of metals and semiconductors. For a starship travelling between stars, radiation damage would accumulate slowly but steadily. Protective layers might need to be thicker than anything currently used on spacecraft, and critical components would need redundancy to ensure that failures in one area do not compromise the entire mission. Friction, in the traditional sense, also takes on a different meaning in interstellar space. There is no air to create drag as there is in an atmosphere, but there is still a form of resistance caused by interactions with the interstellar medium. Each collision with an atom or dust grain transfers a tiny amount of momentum, gradually reducing the spacecraft's speed. Over very long distances, this effect could become noticeable, particularly for lighter spacecraft travelling at extremely high speeds. In most realistic scenarios, the drag from the interstellar medium is small compared to other forces, but it cannot be ignored entirely. Engineers must calculate how much shielding and structural reinforcement are required, and how these choices influence the spacecraft's mass and energy requirements. The front of a starship, the portion facing the direction of travel, would endure the greatest stress. Many proposed designs include a heavily armoured forward shield, sometimes made of layered materials designed to absorb impacts gradually. Some concepts even suggest placing a cloud of fine particles ahead of the spacecraft, released deliberately so that incoming dust grains collide with this cloud first, breaking apart before reaching the main hull. Such ideas illustrate how seriously these challenges are taken. The problem is not merely theoretical. Every collision at relativistic speeds carries real consequences, and the spacecraft must be prepared to withstand them continuously for years. Heat also arises from another source that is easy to overlook: the very act of compressing radiation and particles in the direction of motion increases their energy. As a spacecraft moves faster, the light and cosmic radiation ahead of it become more energetic due to relativistic effects. Photons that would normally be harmless can shift into higher energy ranges, contributing to heating and radiation exposure. This means that shielding must protect not only against physical impacts, but also against increasingly energetic radiation concentrated in the direction of travel. Layers of material, magnetic fields, or combinations of both may be required to reduce exposure to safe levels. Protecting a spacecraft from these effects is not only a matter of engineering, it is also a matter of long-term reliability. Systems must function not for days or months, but for decades. Materials must retain their strength, seals must remain intact, and electronics must continue operating despite constant exposure to radiation and temperature variations. Testing such systems on Earth presents its own difficulties. It is possible to simulate radiation and vacuum conditions, but reproducing decades of exposure to interstellar conditions in a laboratory is far more challenging. Engineers must rely on models, accelerated testing, and cautious design margins, all of which add to the complexity of planning an interstellar mission. Human passengers introduce additional requirements. Living organisms are sensitive to temperature, radiation, and environmental changes. The interior of a spacecraft must remain stable and comfortable, even as the exterior endures extreme conditions. Thermal insulation, redundant life support systems, and careful monitoring would all be essential. And then there is the issue of micrometeoroids and larger particles. While interstellar space is sparse, it is not perfectly uniform. Occasionally larger grains or fragments may be encountered. At high speed, even a particle the size of a grain of sand could release significant energy upon impact. Detecting and avoiding such hazards in advance would be extremely difficult, because they are small and often invisible against the background of space. Some proposed spacecraft designs include forward-facing sensors capable of detecting particles ahead of the ship, allowing small course adjustments to avoid collisions. Others consider using electromagnetic fields to deflect charged particles before they reach the hull. Each approach adds layers of complexity and requires additional energy and equipment. All of these protective measures reinforce a pattern that has appeared repeatedly in our discussion. Every solution to one problem tends to create new challenges. Shielding increases mass. Increased mass requires more energy to accelerate. More energy requires more fuel or larger power systems. Larger systems generate more heat, which must be dissipated. The interconnected nature of these constraints is one of the reasons why the first journeys to another star are likely to be one way. Reducing the requirements of a return trip allows designers to simplify propulsion, reduce fuel mass, and focus resources on survival and protection during the outward journey. It is also worth remembering that interstellar travel does not occur in isolation. The spacecraft must be built, launched, and assembled using resources from Earth or near-Earth space. The more massive and complex the ship becomes, the more difficult and expensive it is to construct and launch. Limiting the mission to a one-way voyage reduces these burdens, making the entire endeavour more feasible. As we think about these challenges, it becomes clear that travelling between stars is not merely a matter of reaching high speeds. It is a matter of enduring the journey, of protecting both machines and people from an environment that, while sparse, becomes hazardous at relativistic velocities. Heat, friction, and radiation are not dramatic obstacles in the sense of sudden catastrophes. They are gradual forces, persistent and cumulative, acting over years and decades. Designing systems that can withstand such conditions requires patience, precision, and a deep understanding of the physics involved. If shielding, propulsion, and life support systems all add mass and complexity, what kinds of propulsion technologies could realistically provide the energy needed to accelerate such a spacecraft in the first place? And which of those technologies might be capable of carrying a vessel fast enough to make the journey between stars possible at all? To move any spacecraft at all, something must be pushed backward. That simple principle, rooted in the conservation of momentum, sits quietly behind every launch ever performed, from the earliest experimental rockets to the vehicles that carried astronauts to the moon. Fuel burns, hot gas expands, and the spacecraft moves in the opposite direction. It is such a familiar process that it is easy to forget how demanding it becomes when the goal is not merely to reach orbit or even another planet, but to cross the immense gulf between stars. The farther and faster a spacecraft must travel, the more demanding propulsion becomes. And when engineers begin to examine what would actually be required to reach even the nearest star within a human lifetime, they quickly discover that the propulsion methods we use today are not simply insufficient. They belong to an entirely different scale of capability. The most familiar type of propulsion is chemical rocketry. Chemical rockets rely on energy released by chemical reactions, typically the combustion of hydrogen and oxygen or other fuels and oxidizers. These reactions release large amounts of energy by everyday standards, enough to lift hundreds of tons off the surface of Earth and send spacecraft across the solar system. Chemical propulsion is powerful, reliable, and well understood, which is why it remains the backbone of modern space flight. Yet chemical energy has strict limits. The amount of energy released per kilogram of fuel is determined by the strength of chemical bonds, and those bonds store far less energy than nuclear reactions. Even the most efficient chemical rockets produce exhaust velocities of only a few kilometers per second. That is sufficient for escaping Earth's gravity and reaching nearby planets, but it is far too slow for interstellar travel. To understand why, consider what happens when you attempt to increase speed using chemical propulsion. The rocket equation ensures that achieving higher velocities requires exponentially more fuel. For the speeds needed to reach another star in less than thousands of years, the amount of chemical fuel required would exceed the mass of any practical spacecraft by an enormous margin. A chemical rocket designed for such a mission would need to be so large and so dominated by fuel that the payload would become negligible. Because of this, chemical propulsion is generally considered unsuitable for interstellar missions, at least for the main phase of acceleration. It may still play a role in launching components from planetary surfaces or maneuvering within star systems, but the long cruise between stars demands something more energetic. This leads naturally to nuclear propulsion, which offers much higher energy densities. Nuclear reactions release energy not from chemical bonds, but from the nuclei of atoms themselves, and the energy available per unit mass is millions of times greater than that of chemical fuels. One of the simplest nuclear propulsion concepts is the nuclear thermal rocket. In this design, a nuclear reactor heats a propellant, usually hydrogen, to extremely high temperatures and expels it through a nozzle to produce thrust. Because the exhaust velocity is higher than in chemical rockets, nuclear thermal propulsion can achieve greater efficiency and higher speeds. Nuclear thermal rockets were studied extensively during the 20th century, and experimental reactors were even tested. Although none have yet flown in space, the technology is considered feasible. For missions within the solar system, nuclear thermal propulsion could significantly reduce travel times. However, even nuclear thermal rockets fall short of what is needed for interstellar travel. Their exhaust velocities, while higher than chemical rockets, are still too low to reach a significant fraction of the speed of light without requiring impractically large amounts of propellant. More ambitious concepts involve nuclear fusion, the process that powers stars. Fusion releases enormous amounts of energy by combining light atomic nuclei into heavier ones. In principle, a fusion-powered spacecraft could achieve much higher exhaust velocities, making interstellar travel more plausible. Several designs for fusion-driven starships have been proposed over the decades. Some involve pulsed fusion explosions behind a spacecraft, using magnetic fields or shock absorbers to convert the energy of each pulse into forward motion. Others envision continuous fusion reactions driving high-speed plasma exhaust. These ideas are scientifically sound in principle, but fusion itself remains a challenging technology even on Earth. Creating and sustaining controlled fusion reactions requires extreme temperatures and pressures, and building reactors that operate reliably for years in space would be a formidable engineering task. Nevertheless, fusion propulsion remains one of the more promising possibilities for future interstellar missions. Beyond fusion lies an even more energetic possibility: antimatter. When matter and antimatter meet, they annihilate completely, converting their mass into energy according to Einstein's equation. This process releases far more energy per unit mass than either chemical or nuclear reactions. In theory, antimatter propulsion could achieve exhaust velocities high enough to reach substantial fractions of the speed of light. A relatively small amount of antimatter could provide enormous thrust, making it an appealing concept for interstellar travel. Yet antimatter presents challenges of its own. Producing antimatter requires enormous amounts of energy, far more than the energy ultimately released when it is used. Current facilities can create only tiny quantities, measured in nanograms, and storing antimatter safely requires complex magnetic traps to prevent it from touching ordinary matter. Scaling this technology to the levels required for propulsion would require breakthroughs in production, storage, and handling. Even if those breakthroughs occur, the safety considerations alone would be significant. A containment failure involving large quantities of antimatter would release energy comparable to a major explosion. Because of these difficulties, antimatter propulsion remains largely theoretical, though it continues to be studied as a long-term possibility. There are also hybrid concepts that combine different propulsion methods. A spacecraft might use one system for initial acceleration, another for cruising, and a third for deceleration. For example, a light sail propelled by powerful lasers from the solar system could accelerate a spacecraft to high speed without requiring onboard fuel. Later, magnetic sails or other mechanisms might be used to slow the spacecraft by interacting with the interstellar medium or the stellar wind of the destination star. Each of these methods attempts to address the central challenge of propulsion, providing enough energy to reach high speeds without requiring the spacecraft to carry an impractical amount of fuel. Even with advanced propulsion, however, limits remain. The speed of light cannot be exceeded, and the energy required to approach that speed increases steeply. This means that there is always a trade-off between speed, mass, and energy. Faster travel requires more energy. Carrying more energy usually means carrying more mass. Carrying more mass requires more thrust, which in turn requires more energy. This cycle is unavoidable because it arises from fundamental physical laws, not from limitations of engineering alone. Another constraint is the reliability of propulsion systems over long durations. A starship's engines might need to operate for months or years during acceleration and deceleration phases. They must function flawlessly in the harsh environment of space, exposed to radiation, temperature extremes, and the gradual wear caused by energetic particles. Repairing such systems would be difficult, especially far from Earth. Redundancy and fault tolerance would be essential, but these features add mass and complexity, reinforcing the recurring theme that every solution carries a cost. Propulsion also determines the structure of the spacecraft itself. Engines capable of producing high thrust or high exhaust velocities may require large radiators to dissipate waste heat, heavy shielding to protect the crew from radiation, and extensive fuel or propellant storage. The spacecraft becomes not just a vehicle, but a carefully balanced system in which propulsion, life support, and protection are tightly integrated. The more closely engineers examine these requirements, the clearer it becomes that designing a spacecraft capable of both reaching another star and returning is vastly more difficult than designing one that travels in a single direction. Eliminating the need for return fuel reduces the total mass dramatically, making the mission more achievable. There is also a strategic aspect to consider. The first interstellar missions may focus on establishing a permanent presence rather than conducting exploratory round trips. A one-way mission could carry equipment, habitats, and supplies intended to support long-term settlement, rather than reserving mass and energy for the journey home. This approach resembles some of the earliest human migrations on Earth. When small groups crossed oceans or continents in ancient times, they often did so without expecting to return. They carried what they needed to survive and to build new lives in unfamiliar places. Interstellar travel, if it occurs, may follow a similar pattern, shaped not only by human ambition, but also by the constraints of physics. All of these considerations highlight an important truth. Propulsion is not merely a technical detail. It defines what kinds of journeys are possible, how long they take, and whether returning home is practical. Chemical propulsion can carry us to nearby planets. Nuclear propulsion may carry us farther and faster within the solar system. Fusion or antimatter might one day make interstellar voyages feasible. But even the most advanced propulsion concepts do not eliminate the fundamental costs of acceleration, deceleration, and long-term survival in deep space. They reduce those costs, perhaps dramatically, but they do not make them vanish. Long before anyone seriously calculated the details of interstellar missions, a simple question began to appear in scientific discussions. If carrying fuel is the greatest obstacle to reaching another star, what would happen if a spacecraft did not carry most of its fuel at all? What if the energy needed for acceleration could be supplied from a distance, leaving the spacecraft itself far lighter and easier to push to high speed? That question leads to one of the most intriguing propulsion ideas ever proposed: beamed propulsion, often paired with structures known as light sails. Unlike rockets, which push themselves forward by expelling mass, a light sail moves by receiving momentum from outside sources, usually in the form of light or other electromagnetic radiation. At first glance, the idea sounds almost delicate, as if something as intangible as light could hardly move a spacecraft. But light, despite having no rest mass, carries momentum. When photons strike a surface and reflect, they transfer a tiny amount of force. On everyday scales, this force is so small that it goes unnoticed. Yet in the vacuum of space, where there is no air resistance and even a gentle push can accumulate over long periods, that tiny force can gradually build up speed. The principle is not merely theoretical. Solar sails, which use sunlight itself as the source of momentum, have already been tested in space. These sails are large, thin, reflective membranes that capture the pressure of sunlight. The acceleration they provide is extremely small, but it is continuous, and over time a spacecraft can reach higher speeds than would be possible with limited onboard fuel. Sunlight alone, however, is far too weak to accelerate a spacecraft to the velocities required for interstellar travel. To reach a significant fraction of the speed of light, a much more powerful source of radiation would be needed. This is where beamed propulsion enters the picture. In a beamed propulsion system, powerful lasers or microwave transmitters located far behind the spacecraft direct an intense beam of energy onto a sail. The beam provides a steady push, accelerating the spacecraft without requiring it to carry large quantities of propellant. As long as the beam remains focused on the sail, acceleration continues. This approach offers a profound advantage. Because the spacecraft does not need to carry most of its fuel, its mass can be dramatically reduced. Lower mass means less energy is required to accelerate it to high speed. The tyranny of the rocket equation, which makes traditional rockets so inefficient for interstellar travel, becomes far less severe. Of course, solving one problem introduces others. Generating and focusing an energy beam powerful enough to accelerate a spacecraft across interstellar distances is an enormous challenge. The transmitters would need to be vast, possibly spanning kilometers, and they would require immense amounts of power. Such systems might be built in orbit around the Sun or on the surface of the Moon, where large structures can be assembled without the constraints of Earth's gravity. The beam itself must remain tightly focused over enormous distances. As light travels, it naturally spreads out, a phenomenon known as diffraction. Even the most precisely engineered beam will gradually widen, reducing the intensity of the radiation reaching the sail. Designing systems that can maintain a narrow beam over millions of kilometers, or even billions, is an area of ongoing research. Another challenge lies in controlling the spacecraft's trajectory. A light sail must remain precisely aligned with the incoming beam. Even small deviations could reduce acceleration or cause the sail to drift off course. Guidance and stabilization systems would need to operate continuously, adjusting the sail's orientation with extreme precision. Despite these difficulties, beamed propulsion remains one of the most promising concepts for achieving the high speeds required for interstellar travel. Some proposals envision sending very small probes, perhaps no larger than a postage stamp, attached to ultralight sails. Because the mass of these probes would be tiny, even a relatively modest beam could accelerate them to significant fractions of the speed of light. Projects studying such ideas have suggested that miniature spacecraft might one day be sent to nearby stars within a few decades of travel time. These probes would not carry humans or large instruments, but they could transmit valuable data about distant star systems, providing the first close-up observations of worlds beyond our solar system. Scaling this concept up to human missions is far more difficult. Larger spacecraft require larger sails and much more powerful beams. The energy demands increase dramatically, and the engineering challenges multiply. Yet the underlying principle remains attractive because it removes one of the greatest burdens of interstellar travel, the need to carry vast amounts of fuel. Leaving fuel behind, however, creates a new and serious difficulty. Accelerating a spacecraft with a beam is only half the journey. Once the spacecraft approaches its destination, it must slow down. Without deceleration, it would pass through the target star system at enormous speed, unable to enter orbit or land on any planets. Slowing down requires energy, just as accelerating does. If there is no powerful beam waiting at the destination, the spacecraft must rely on onboard propulsion or other methods to reduce its speed. This brings back the problem of fuel, although in a different form. Some proposed solutions involve using magnetic sails or electric sails to interact with the stellar wind of the destination star, gradually slowing the spacecraft over time. These methods rely on the presence of charged particles streaming outward from stars, which can exert a small but continuous force on large electromagnetic structures. Deceleration would be slow, perhaps taking years or decades, but it might be sufficient to allow the spacecraft to enter orbit. Another idea involves using the sail itself for braking. If the spacecraft approaches a star from the correct angle, it may be possible to use the pressure of the star's light to slow down, much as sunlight can accelerate a sail when departing from a star system. This technique, sometimes called photogravitational braking, combines radiation pressure and gravitational effects to reduce velocity without large amounts of fuel. These methods are promising but complex. They require precise navigation and careful timing, and they may not provide enough braking force for larger spacecraft. For early missions, especially those carrying humans, relying entirely on such techniques might be risky. Because of this, many realistic scenarios suggest that the first large interstellar spacecraft, accelerated by beamed propulsion, would not be designed to return. They would carry enough equipment and supplies to sustain life at the destination, rather than reserving mass and energy for the journey home. This reinforces the central theme that has been emerging throughout our discussion. The laws of physics do not forbid reaching another star, but they impose constraints that shape how such journeys must be planned. Beamed propulsion makes it easier to leave, but it does not make it equally easy to come back. There is also the question of infrastructure. A beamed propulsion system capable of accelerating large spacecraft would represent one of the most ambitious engineering projects in human history. It would require enormous power sources, vast arrays of transmitters, and precise coordination over long distances. Building such a system would likely take decades and involve the combined efforts of many nations or even the entire planet. Once built, however, such infrastructure could launch multiple missions, gradually sending probes, cargo, and eventually human travelers toward nearby stars. Over time, a network of star systems connected by one-way journeys might begin to form, each new destination becoming a starting point for further exploration. In this way, interstellar travel might unfold not as a series of round trips, but as a gradual expansion, step by step, outward from the solar system. Each mission would carry people or machines that would remain at their destination, building new outposts that future travelers might one day visit. There is something quietly fitting about this possibility. Human history on Earth often progressed in a similar way. Explorers crossed oceans and settled new lands, not expecting to return frequently, but intending to establish new homes. The distances between stars are far greater than any ocean, but the underlying pattern may not be entirely different. As engineers and physicists continue to study beamed propulsion and light sails, they are also learning more about the challenges of controlling large, fragile structures in space, managing immense flows of energy, and navigating across distances where communication delays stretch into years. Each of these challenges brings its own lessons, gradually turning ideas that once seemed purely theoretical into subjects of serious research. If a spacecraft can be accelerated to high speed by leaving fuel behind and riding a beam of energy outward, what happens when it finally approaches another star and must shed that enormous velocity, slowing down enough to remain there rather than continuing endlessly into the darkness beyond? Reaching high speed is only half of any journey through space, and in some ways it is the easier half to imagine. Acceleration has a certain simplicity to it. Engines fire, energy is released, and velocity gradually increases. The mathematics is demanding, the engineering even more so, but the direction of the problem is clear. Push forward long enough, and you will eventually be moving fast. Stopping, however, is different. Stopping means removing every bit of kinetic energy that was so difficult to acquire in the first place. A spacecraft approaching another star at a significant fraction of the speed of light carries an enormous amount of energy in its motion, and that energy must be dealt with carefully. It cannot simply disappear. Physics requires that it be transferred somewhere, converted into another form or carried away. To appreciate the scale of this challenge, it helps to think about energy in everyday terms. When a car brakes, its kinetic energy is converted into heat through friction between the brake pads and the wheels. That heat dissipates into the surrounding air. The process feels ordinary because the energies involved are modest, and the atmosphere carries the heat away efficiently. A spacecraft in interstellar space does not have that luxury. There is no air to absorb heat, no road to provide friction, and no convenient environment to carry energy away. If a spacecraft travelling at high speed wishes to slow down, it must rely on propulsion systems, electromagnetic interactions, or gravitational effects, all of which are far more complicated than pressing a brake pedal. Consider a spacecraft travelling at 10% of the speed of a light. The kinetic energy of such a vessel is immense, far greater than the energy released by most terrestrial power plants over many years. To slow down, the spacecraft must expend energy comparable to what was required to accelerate in the first place. This means firing engines in reverse, deploying sails, or using other mechanisms capable of exerting force over long periods. If the spacecraft carried all the fuel needed for both acceleration and deceleration, its mass would increase dramatically, making the entire mission far more difficult. This is why the problem of slowing down is often cited as one of the central obstacles to interstellar travel. It is not enough to reach another star. You must also arrive in a way that allows you to remain there. Without deceleration, the spacecraft would simply pass through the destination system at enormous speed. Even a brief encounter would last only hours or days, far too short a time for meaningful exploration, and certainly too short for establishing a permanent presence. The ship would continue onward into interstellar space, carried by inertia, with no practical way to return. Several methods have been proposed to address this challenge, each with advantages and limitations. One approach involves carrying fuel specifically for deceleration. This is the most straightforward solution in principle. Engines fire in the opposite direction, gradually reducing velocity until the spacecraft can enter orbit around a star or planet. Yet this approach brings us back to the rocket equation and the problem of mass. Every kilogram of fuel carried for braking must be accelerated during the outbound journey. That additional mass requires more energy to accelerate, which in turn requires more fuel, creating a cycle that quickly becomes impractical for large spacecraft. Another possibility involves using large sails to interact with the radiation or stellar wind of the destination star. Just as sunlight can push a sail outward, it can also slow a sail that approaches from the correct direction. This technique relies on the pressure exerted by photons and charged particles streaming away from the star. The force produced by radiation pressure is small, but it acts continuously. Over months or years, it can reduce a spacecraft's speed significantly. The difficulty lies in deploying sails large enough to generate meaningful braking forces and ensuring that they can survive the stresses of interstellar travel. Such sails might need to span kilometers, constructed from materials that are both extremely light and extraordinarily strong. Magnetic sails offer another intriguing possibility. Instead of relying on a physical surface, a magnetic sail uses powerful magnetic fields to deflect charged particles in the stellar wind. As these particles are redirected, they transfer momentum to the spacecraft, gradually slowing it down. This method has the advantage of avoiding the need for fragile physical sails, but it introduces other challenges. Generating and maintaining large magnetic fields requires energy and complex equipment. The strength of the braking force depends on the density and speed of the stellar wind, which vary from star to star. Deceleration using this method could take many years, requiring precise navigation and long-term reliability. Gravitational braking is another technique that may play a role. By passing close to a star or planet, a spacecraft can use gravity to alter its trajectory and reduce its speed relative to the central body. This method, known as a gravity assist when used for acceleration, can also be applied in reverse to help slow down. However, gravity alone cannot remove all the kinetic energy of a spacecraft arriving from interstellar space at high velocity. It can assist in the process, but additional braking methods would still be required to achieve orbit or landing. Each of these techniques illustrates a common theme. Slowing down requires time, distance, and careful planning. Deceleration cannot be instantaneous. It must occur gradually over millions or billions of kilometers, long before the spacecraft reaches the inner regions of the destination system. This means that navigation becomes even more critical than during the outbound journey. The spacecraft must approach the star along a trajectory that allows its braking systems to function effectively. A small error in course or timing could reduce the efficiency of deceleration or even make it impossible to stop. Communication delays add another layer of complexity. If the spacecraft is several light years from Earth, messages take years to travel in either direction. Decisions about braking maneuvers must therefore be made autonomously by onboard systems or by the crew without real-time guidance from mission control. Reliability becomes crucial. Engines, sails, and other braking mechanisms must function after years or decades of exposure to radiation, dust, and thermal stress. A failure during deceleration could leave the spacecraft unable to stop, transforming a carefully planned mission into an unintended flyby. There is also the human dimension to consider. For travelers aboard a starship, the deceleration phase would mark the beginning of arrival, the long transition from the emptiness between stars to the gravitational influence of a new sun. It would be a period of anticipation and uncertainty, perhaps lasting months or years, during which the success of the mission would depend on systems that must perform exactly as designed. From an engineering perspective, eliminating the need for a return trip simplifies the problem significantly. A one-way mission requires only enough fuel or braking capability to slow down once. A round trip requires at least twice as much deceleration and acceleration, doubling or even tripling the energy and mass requirements. This is one of the key reasons why many scientists believe the first journeys to another star will be one way. The difference between stopping once and stopping twice is enormous when velocities are measured in tens of thousands of kilometers per second. It is also worth remembering that the destination itself offers no guarantee of safety or suitability. The star system reached may not contain habitable planets. Conditions may be harsh or unpredictable. The travelers must be prepared to adapt, to use whatever resources are available, and to build new habitats if necessary. Planning for a return journey under such uncertain conditions adds yet another layer of difficulty. All of these factors combine to shape how interstellar missions are envisioned. Acceleration may capture the imagination, but deceleration determines whether the journey can truly be called an arrival. Without the ability to slow down, reaching another star is little more than passing by it. By the time a starship has slowed enough that a distant sun begins to dominate the sky ahead, the nature of the journey changes in a subtle but important way. Up to that point, the spacecraft has been moving through interstellar space, influenced only weakly by the gravity of distant stars. Motion in that region is largely a matter of inertia and propulsion. Once a star grows near, however, gravity begins to take control of the situation, and the problem is no longer simply one of speed, but of orbits and energy. Gravity is often described as an attractive force, but in orbital mechanics it is more useful to think of gravity as a sculptor of paths. Objects moving through a gravitational field follow curves determined by their speed and direction. A spacecraft approaching a star does not simply fall straight inward unless its velocity is extremely low. Instead, it traces a long sweeping arc, bending gradually under the influence of the star's mass. For a mission arriving from interstellar space, this means that reaching the vicinity of another star is not the same as stopping there. A spacecraft might pass within millions of kilometers of a star and still continue outward again, because its velocity remains too high to be captured into orbit. To remain in the system, the spacecraft must reduce its speed relative to the star to a very specific range, one that allows gravity to hold it in a stable trajectory rather than letting it escape back into the darkness between stars. This requirement introduces another layer of energy considerations. When engineers speak about stopping in space, they do not usually mean bringing a spacecraft to a complete halt in an absolute sense. There is no universal rest frame in the universe. Everything is moving relative to something else. What they mean is reducing velocity relative to a particular object, in this case, a star or a planet. The amount of energy that must be removed to achieve this depends on the spacecraft's speed as it approaches. Kinetic energy increases with the square of velocity, and at relativistic speeds it grows even more steeply. A vessel arriving at a significant fraction of the speed of light carries an immense reservoir of energy in its motion, energy that must be dissipated or redirected before the spacecraft can enter orbit. Entering orbit itself is a delicate balance. To remain in orbit around a star, a spacecraft must move fast enough that it does not fall inward, yet slow enough that it does not escape outward. This balance between gravitational attraction and forward motion defines every orbit, from the path of the Moon around Earth to the trajectories of planets around the Sun. If the spacecraft arrives too fast, gravity cannot capture it. If it arrives too slowly, it risks falling inward toward the star, where intense heat and radiation could become a serious hazard. The target velocity range is narrow compared with the enormous speeds involved in interstellar travel, which means that deceleration must be both substantial and precise. One way to visualize this is to imagine rolling a ball across a shallow bowl. If the ball is rolled gently, it settles near the center. If rolled too hard, it climbs the opposite side and escapes the bowl entirely. A spacecraft approaching a star faces a similar situation, except that the bowl is not a physical surface but a gravitational well extending across millions of kilometers. Another important factor is that stars are rarely alone. Many stars exist in systems with multiple planets, moons, and sometimes companion stars. Each of these bodies exerts gravitational influence, creating a complex environment of interacting forces. Navigating through such a system requires careful calculations and continuous adjustments to trajectory. Consider what would be required for a spacecraft to enter orbit around a planet in another star system. First, it must reduce its speed relative to the star itself. Then it must adjust its trajectory to intersect the orbit of the target planet at the right time and angle. Finally, it must slow down further to be captured by the planet's gravity. Each of these steps requires energy, and each one depends on the successful completion of the previous stage. A small error early in the process can grow into a large deviation by the time the spacecraft reaches the inner regions of the system. Gravity assists, sometimes called slingshot maneuvers, can help in certain situations. By passing close to a massive object, a spacecraft can exchange energy and momentum with that object, altering its speed and direction. Within our solar system, gravity assists have been used to send probes to the outer planets, using relatively modest amounts of fuel. However, gravity assists are not a complete solution for interstellar arrivals. They can help fine-tune trajectories and reduce the amount of fuel needed for certain maneuvers, but they cannot remove the enormous kinetic energy associated with relativistic speeds. The spacecraft must still shed most of that energy through propulsion or other braking mechanisms before gravity can play its role effectively. There is also the matter of heat and radiation near a star. As a spacecraft approaches, the intensity of starlight increases dramatically. Solar radiation pressure becomes stronger, which can be useful for braking if sails are employed, but thermal loads also increase. Surfaces facing the star must withstand rising temperatures, and cooling systems must be capable of handling the additional heat. If the destination star is more active than our Sun, as many red dwarfs are, the spacecraft may encounter strong stellar flares and bursts of charged particles. These events can produce intense radiation that must be shielded against, particularly if human passengers are aboard. All of this means that arrival is not a single event but a long, carefully planned sequence. Deceleration may begin years before the spacecraft actually reaches the star. Sails or engines might operate continuously over millions of kilometers, gradually reducing velocity while the star grows brighter and larger in the forward view. During this period, the crew or onboard systems must monitor trajectories, adjust orientation, and ensure that all critical systems continue functioning after decades of travel. The margin for error is small, and the stakes are high. Energy management remains central throughout this process. The kinetic energy removed from the spacecraft does not simply vanish. Engines expel propellant at high speed, sails transfer momentum to photons or particles, and braking systems convert motion into other forms of energy that must be carried away. In many proposed mission profiles, the energy required to slow down is nearly as large as the energy required to accelerate in the first place. This symmetry is unavoidable. Physics does not provide discounts for the return leg of a journey, and it does not make stopping any easier than starting. This is one of the reasons why the concept of a one-way mission continues to appear in serious discussions of interstellar travel. Eliminating the need to accelerate back to high speed and then decelerate again upon arrival at Earth reduces the total energy budget enormously. The spacecraft can be designed to carry only what is needed to reach the destination and remain there. For the travelers, this changes the meaning of the journey. They would not be explorers expecting to return home, but settlers embarking on a permanent relocation. Their destination would become their new world, and the star behind them would gradually fade into memory. There is also a broader perspective to consider. In the vast timescales of the universe, stars themselves are not fixed. They move through the galaxy, orbiting the galactic center over hundreds of millions of years. A spacecraft traveling for decades or centuries must account for this motion, aiming not at where a star is now, but at where it will be when the spacecraft arrives. Navigation over such distances requires extraordinary precision. Small uncertainties in velocity or direction can translate into enormous deviations over light years of travel. Instruments must be capable of measuring positions and velocities with extreme accuracy, and course corrections may be needed even in the emptiness between stars. All of these challenges reinforce the idea that arrival is as complex and demanding as departure. Gravity, which seems so gentle and predictable in everyday life, becomes a powerful and sometimes unforgiving force when combined with high velocities and large distances. Yet there is also something quietly elegant about orbital motion. Once a spacecraft has reduced its speed sufficiently and entered a stable orbit, It can remain there indefinitely with little or no expenditure of energy. Planets orbit their stars for billions of years, guided by gravity alone. A starship once captured would share in that same graceful motion. From that point onward, the focus of the mission would shift. The long years of travel would give way to exploration, construction, and the slow process of adapting to a new environment. The energy once devoted to propulsion would be redirected towards sustaining life, building habitats, and studying the new system in detail. But reaching that point requires solving the problem of stopping, and stopping requires confronting the realities of gravity, energy, and orbital mechanics. These are not obstacles in the sense of barriers that cannot be crossed, but they are constraints that shape every decision in the design of an interstellar mission. Long after the engines fall silent and the long acceleration phase has ended, another reality of interstellar travel begins to shape daily life aboard a spacecraft, and it is a reality that cannot be shielded against or engineered away. Distance does not only separate places, it separates moments. Information itself must cross that distance, and information travels no faster than light. This simple fact has consequences that are easy to underestimate at first. On Earth, communication feels almost instantaneous. Messages cross continents in fractions of a second. Video calls allow conversations to flow naturally, with no noticeable delay. Even communications with spacecraft in orbit feel immediate, the lag so small that it rarely enters our awareness, but the farther signals must travel, the more noticeable the delay becomes. When astronauts travelled to the Moon, radio messages took about 1.5 seconds to reach Earth. Conversations required brief pauses, a rhythm of speaking and waiting that felt unfamiliar but manageable. Communication with spacecraft near Mars can involve delays of several minutes, depending on the positions of the planets. Engineers and astronauts adapt by speaking in short, clear transmissions and waiting patiently for replies. Now imagine extending that delay from minutes to years. A spacecraft orbiting Proxima Centauri would be more than 4 light-years away. Any message sent to Earth would take over 4 years to arrive. A reply would take the same amount of time to return. A single exchange of questions and answers would span nearly a decade. This is not a limitation of technology. It is a limitation of physics. No signal, no matter how powerful or sophisticated, can outrun light in a vacuum. Radio waves, lasers, and every other form of electromagnetic communication travel at exactly the same ultimate speed. For the crew of an interstellar mission, this means that real-time communication with Earth is impossible. Instructions cannot be requested and received in the ordinary sense. Emergencies cannot be discussed with mission control while they are happening. Decisions must be made locally, relying on onboard expertise and systems. In practical terms, a starship must function as an independent world, capable of solving its own problems without outside assistance. Engineers on Earth might analyze telemetry and send advice, but that advice would always arrive years after the situation had occurred. By the time a response came back, the circumstances that prompted it might have changed completely. This independence is not entirely new. Deep space probes already operate with a degree of autonomy. Spacecraft exploring the outer planets must carry software capable of handling unexpected events, adjusting trajectories, and protecting sensitive equipment without waiting for instructions. Interstellar missions would extend this principle much further, requiring systems capable of managing almost every aspect of operation on their own. Communication delays also affect navigation and coordination. Tracking a spacecraft across light-years of distance requires careful measurements and predictions. Observers on Earth would always see the spacecraft as it was years ago, not as it is in the present moment. Commands sent to adjust course would arrive years later, by which time the spacecraft might already have executed several maneuvers of its own. Because of this, navigation must be largely autonomous, based on onboard observations of stars, pulsars, and other reference points. Instruments capable of precise measurement would guide the spacecraft. while communication with Earth would serve more as a long-term exchange of information rather than real-time control. There is also a psychological dimension to communication delays. For travellers, knowing that every message from home is years old can change the way those messages feel. News about events on Earth would arrive long after they had happened. Celebrations, discoveries and losses would be known only in retrospect, filtered through years of silence. Imagine receiving a message describing a scientific breakthrough, only to realise that the breakthrough occurred nearly a decade earlier by the time the message reaches you, or learning about changes in the world that are already part of history by the time you hear of them. The sense of connection to Earth would remain, but it would become more distant, more reflective, less immediate. The same would be true in the opposite direction. Messages sent by the crew would reach Earth years later, describing experiences that had already passed into memory. Conversations would become more like exchanges of letters than spoken dialogue, thoughtful and patient rather than spontaneous. Over long periods, this separation in time might gradually reshape the relationship between travellers and those who remain behind. Cultures evolve, languages shift, and societies change. Even within a few decades, the world can transform in ways that are difficult to predict. For travellers moving between stars, the pace of change on Earth might feel accelerated, as if history were unfolding more quickly than they could follow. Time dilation could amplify this effect. If the spacecraft travels at relativistic speeds, the crew may experience fewer years than pass on Earth. By the time they arrive at their destination, the civilization that launched them could be far older, perhaps very different from what they remember. Communication itself would also require careful planning and powerful equipment. Signals weaken as they spread through space, and over light years of distance they become extremely faint. Large antennas or laser transmitters would be needed to send and receive messages reliably. Even then, data rates would likely be limited, making communication slow and deliberate rather than continuous. Error correction would become essential. Cosmic radiation and interstellar plasma can interfere with signals, introducing noise and distortions. Messages might need to be transmitted repeatedly to ensure that they are received correctly. Patience would become a routine part of communication, as both sides wait years to confirm that information has arrived intact. Despite these challenges, communication across light years is not impossible. Radio telescopes on Earth already detect signals from spacecraft billions of kilometers away, and laser communication systems are being developed to transmit data more efficiently over large distances. With sufficiently large transmitters and receivers, exchanging information between stars is technically feasible, though slow. There is also the possibility of sending physical messages in a sense. Data storage devices carried aboard supply ships or probes could deliver vast amounts of information upon arrival, far more than could be transmitted by radio alone. Such methods would not replace communication but might supplement it, allowing large libraries of knowledge, culture, and history to accompany travellers to distant systems. Over time, a network of interstellar communication might develop, with relay stations or colonies acting as intermediate points. Messages could hop from one system to another, reducing delays between neighbouring stars even as the total distance from Earth grows. Such a network would take generations to build, but it could gradually transform the way information flows across the galaxy. Yet even with such networks, the fundamental limit would remain. The speed of light would still govern how quickly information can travel. Delays measured in years or decades would remain a normal part of life for anyone living beyond the solar system. This has profound implications for the nature of exploration and settlement. A colony around another star would not be an extension of Earth in the way a distant city is. It would be a separate society, shaped by its own experiences and challenges, evolving in parallel with the civilization that sent it. The same independence that makes a one-way journey practical from an engineering perspective also makes it inevitable from a cultural perspective. Distance and communication delays ensure that travellers cannot remain closely tied to the world they left behind. Over time, their identity would shift, shaped more by their new environment than by memories of Earth, and yet there would still be a connection, however faint. Messages, images, and recordings would cross the darkness, carrying news, discoveries, and stories. Even separated by years of silence, people would still be able to share knowledge and ideas, maintaining a thread of continuity across the immense distances of space. As these realities settle in, it becomes clear that communication across light years is not merely a technical challenge. It is a transformation in how human beings relate to one another, in how societies remain connected, and in how history itself is experienced. The farther we travel, the more the universe reveals its true scale, not only in kilometers but in moments. Every signal, every message, every piece of information must make the same long journey through space, bound by the same universal speed limit. Seen from a certain perspective, motion through space is never simply motion through space. It is also motion through time, and once distances and velocities become large enough, the connection between the two becomes impossible to ignore. Earlier we explored how time dilation changes the rate at which time passes for travellers moving at high speed. Now it becomes important to look at a deeper consequence of that same physics, something less obvious but far more decisive for the idea of returning home. Relativity does not just alter clocks, it alters the sequence of events experienced by different observers, and over long journeys, this difference grows so large that the path taken through space-time begins to matter more than the starting point itself. A long interstellar voyage is not like a long walk in which you can simply retrace your steps. It is more like following a path through a flowing river, where the water behind you is never quite the same as it was when you first passed through it. To understand this more clearly, it helps to think about what a journey really is in physical terms. A spacecraft travelling between stars traces a path through space-time, a continuous sequence of positions and moments. Earth, meanwhile, traces its own path, orbiting the Sun, moving through the galaxy, and continuing forward in time at its own rate. Even if the spacecraft could return to the same location in space, it could never return to the same moment in time. That moment would already be gone, carried away by the steady forward flow of events. This is true for any journey, of course, even those taken at ordinary speeds. If you travel to another city and return, time has passed everywhere, not just where you went. But at relativistic speeds, the difference becomes far more pronounced, because time itself passes at different rates for travellers and those who remain behind. Imagine again the example of two people, one remaining on Earth and the other travelling to another star at high speed. From the traveller's perspective, the journey might take only a few years. From Earth's perspective, decades might pass. When the traveller returns, they do not step back into the world they left. They step into a future that unfolded without them. This is sometimes described using the language of paradox, but there is nothing paradoxical about it. It is simply a consequence of the geometry of space-time. Different paths between two events can involve different amounts of elapsed time, just as different routes between two cities can have different lengths. The traveller's path, involving high speeds and changes in direction, is shorter in time than the path of someone who remained on Earth. What makes this especially significant for interstellar travel is that the longer and faster the journey, the greater this difference becomes. For voyages lasting decades or centuries in Earth's frame of reference, the gap between the traveller's time and Earth's time could grow very large. A return journey might bring the travellers back not to the civilization that launched them, but to one that has evolved far beyond it. This alone gives long voyages a kind of irreversibility, not in the sense that returning is physically impossible, but in the sense that returning cannot restore what has been left behind. The travellers may come back to the same planet, but not to the same world. There is also another, more practical kind of irreversibility that emerges from relativistic travel. Every phase of acceleration and deceleration requires energy, as we have seen. The faster the spacecraft travels, the more energy must be invested, and the more difficult it becomes to repeat the process. Over very long distances, the energy required for a round trip grows so large that designing missions as one-way journeys becomes far more realistic. Relativity reinforces this conclusion in a subtle way, because time dilation reduces the duration of the journey for the travellers, but not for those on Earth. The return leg of the voyage would not merely repeat the outward journey. It would return the travellers to a point in Earth's future that may be separated from their departure by many decades or even centuries. Planning such a mission becomes increasingly complex as the timescales involved grow longer. Communication delays add to this sense of irreversibility. Once a spacecraft is several light years away, decisions made on Earth cannot influence events aboard the ship in any immediate way. The crew must rely on their own judgment, their own resources, and their own ability to solve problems. Over time, the spacecraft becomes less like a vehicle on a mission and more like an independent world, following its own course through both space and history. This independence has consequences that extend beyond engineering. Human societies are shaped by shared experiences, by communication, and by the steady exchange of ideas. When that exchange slows to the pace of years or decades, cultures begin to diverge. Language evolves, customs change, and priorities shift. The travellers and those who remain behind may begin to think of themselves as belonging to different communities, even if they still share a common origin. In this way, the journey becomes irreversible, not only in physical terms, but in social and cultural ones. The longer the distance, and the longer the separation, the more distinct the two societies become. Another aspect of irreversibility arises from the wear and aging of machines and materials. A spacecraft designed for an interstellar voyage must endure years or decades of exposure to radiation, dust impacts, and thermal cycling. Even with the most careful design, components will degrade over time. Systems may fail, repairs may become more difficult, and the margin for error may shrink. A return journey would require the spacecraft to remain fully functional for a period perhaps twice as long as the outward trip. The longer a system must operate without replacement or resupply, the greater the risk of failure. This practical reality adds yet another layer to the argument for one-way missions, especially in the early stages of interstellar exploration. Energy, time, communication, and reliability all combine to create a situation in which long voyages naturally tend toward irreversibility, not because the laws of physics forbid returning, but because the costs and consequences of doing so become increasingly severe. There is also a broader perspective to consider. On cosmic timescales, nothing truly returns to where it once was. Stars move through the galaxy. The galaxy itself moves through the universe. Even the atoms in our bodies are constantly exchanged with the environment. Change is the only constant, and motion through time ensures that every journey leads to a different future than the one imagined at its beginning. For travellers between stars, this truth becomes more visible and more immediate. The sky itself would change slowly as the spacecraft moves, constellations shifting, nearby stars growing brighter or dimmer. The familiar patterns of the night sky seen from Earth would gradually dissolve, replaced by new arrangements of light. By the time the travellers reached another star system, the sun would appear as just another distant star, indistinguishable to the naked eye from countless others. The sense of leaving home would no longer be an abstract idea. It would be written across the sky itself. All of this gives interstellar travel a character very different from any journey in human history. It is not simply a matter of distance, but of transformation. The travellers who arrive will not be the same people who departed, not only because of the passage of time, but because of the experiences and changes that occur along the way. And once a new settlement begins to grow around another star, the idea of returning to Earth may gradually lose its urgency. New relationships, new purposes, and new generations would anchor people to their new world. The journey outward would become part of history, a story told to children who have never seen the planet where it began. In that sense, the irreversibility of long voyages is not only a constraint but also a beginning. It marks the point at which exploration becomes migration, and migration becomes the seed of new civilizations. Yet even as these possibilities unfold, the underlying physics remains quietly present, shaping every decision and every plan. Relativity does not command travellers to stay or to go. It simply defines the structure of space-time, the limits of speed, and the relationship between motion and time. Within those limits, human choices will determine what paths are taken. Inside a spacecraft travelling for decades, the most important resource is not fuel alone, or even oxygen or water, but balance. Every system must operate in a continuous cycle, and every cycle must remain stable for years without interruption. This is the domain of thermodynamics, the branch of physics that describes how energy moves, how heat flows, and how order and disorder change over time. For long-duration spaceflight, thermodynamics is not an abstract set of equations. It becomes the framework that determines whether life can be sustained at all. To understand why, it helps to begin with a simple principle. Energy cannot be created or destroyed. This is the first law of thermodynamics, and it governs everything from the operation of engines to the metabolism of living organisms. On Earth, energy arrives constantly from the sun. Plants convert sunlight into chemical energy, animals eat plants or other animals, and heat radiates back into space. The cycle is vast and continuous, powered by a star that delivers far more energy than life on Earth requires. A spacecraft travelling between stars does not have access to such an abundant external supply. It must carry its energy sources with it, or generate energy in ways that can be sustained for decades. Nuclear reactors are often proposed for this role because they can provide steady power for long periods. Solar panels, so useful within the inner solar system, become far less effective as distance from the sun increases, and in interstellar space they would produce almost no power at all. Whatever the energy source, the spacecraft must carefully manage how that energy is used. Power is needed for life support systems, lighting, heating, cooling, communications, navigation, and possibly artificial gravity or propulsion during certain phases of the mission. Every watt must be accounted for, and every conversion of energy produces heat as a byproduct. Heat, in fact, becomes one of the central challenges of long-duration spaceflight. On Earth, excess heat is easily carried away by air or water. In space, heat can leave only by radiation, which is a much slower process. Radiators must be large and efficient, designed to release infrared radiation into the cold of space. If heat accumulates faster than it can be radiated away, temperatures inside the spacecraft would gradually rise, eventually reaching levels that could damage equipment or endanger the crew. This means that thermal management is not an occasional concern but a continuous one. Systems must monitor temperatures, adjust heat flows, and ensure that no part of the spacecraft becomes too hot or too cold. Even small imbalances, if left uncorrected over years, could grow into serious problems. The second law of thermodynamics introduces another important concept: entropy. In simple terms, entropy measures the tendency of systems to move from order toward disorder. Heat flows naturally from warmer regions to cooler ones. Organised structures tend to break down unless energy is supplied to maintain them. For a spacecraft, this means that maintaining order requires constant effort. Air must be filtered and circulated. Water must be purified and recycled. Waste must be processed. Mechanical parts must be lubricated and maintained. Without continuous input of energy and careful control, the internal environment of the spacecraft would gradually degrade. Closed-loop life support systems are designed to address this challenge. Instead of carrying all the air, water, and food needed for the entire journey, the spacecraft recycles these resources repeatedly. Carbon dioxide exhaled by the crew can be converted back into oxygen through chemical or biological processes. Water can be purified and reused. Organic waste can be processed to recover nutrients. Designing such systems to function reliably for decades is an extraordinary engineering task. On Earth, ecosystems recycle materials naturally, but they are vast and complex, supported by the continuous input of solar energy. A spacecraft must replicate essential parts of these cycles in a much smaller and more controlled environment. Some proposed designs include small agricultural systems or hydroponic gardens, allowing plants to contribute to oxygen production and food supply. Plants also help regulate humidity and provide psychological benefits for the crew, offering a sense of connection to living systems rather than purely mechanical surroundings. However, biological systems introduce their own challenges. They must be carefully balanced to prevent the buildup of harmful microorganisms, nutrient imbalances, or unexpected changes in growth patterns. Maintaining a stable artificial ecosystem over decades would require constant monitoring and the ability to intervene when conditions drift out of balance. Thermodynamics also governs the durability of materials. Over time, metals fatigue, polymers degrade, and electronic components age. Temperature cycles, radiation exposure, and mechanical stress all contribute to gradual wear. Even if each change is small, the cumulative effect over years can be significant. Engineers must therefore design spacecraft with redundancy, meaning that critical systems have backups, and sometimes backups for the backups. Spare parts must be carried, and tools must be available to perform repairs. In some concepts, advanced manufacturing systems such as 3D printers might allow the crew to fabricate replacement components from raw materials stored on board. All of these measures reflect an understanding of entropy. Systems tend to wear down, and maintaining them requires energy, planning, and time. Another thermodynamic consideration involves the storage and use of energy itself. Batteries, capacitors, and other storage systems degrade over time. Chemical fuels may slowly break down. Even nuclear reactors have limits, as fuel is consumed and structural materials are exposed to intense radiation. Long-duration missions must therefore account for how energy availability will change over time. Power systems must be designed not only to meet immediate needs, but to remain reliable after years of operation. Maintenance and replacement of power components may become routine tasks for the crew, as essential as maintaining air or water supplies. Temperature control extends beyond preventing overheating. In the cold of interstellar space, external surfaces can drop to extremely low temperatures, and thermal gradients between different parts of the spacecraft can create mechanical stresses. Materials expand and contract with temperature changes, and repeated cycles can lead to cracks or leaks if not carefully managed. Insulation, heaters, and carefully designed structural connections help mitigate these effects, but they add complexity and mass. Once again, every solution introduces new constraints, reinforcing the interconnected nature of spacecraft design. Human physiology also interacts with thermodynamics in subtle ways. The human body generates heat continuously, and in a confined environment that heat contributes to the overall thermal load. Humidity from breathing and perspiration must be controlled to prevent condensation, which could damage equipment or encourage microbial growth. Air circulation systems must distribute temperature evenly, preventing hot or cold spots. These systems must operate quietly and reliably, because constant noise or vibration could affect the well-being of the crew over long periods. Food storage and preparation introduce additional considerations. Preserving food for decades without spoilage requires careful control of temperature and atmosphere. Freeze-drying, vacuum sealing, and other techniques can extend shelf life, but fresh food production may still be necessary to maintain nutrition and morale. Water, one of the most critical resources, must be recycled with extremely high efficiency. Even small losses over time could become significant. Systems designed for the International Space Station already recycle water from humidity and waste, but interstellar missions would require even higher levels of reliability and efficiency. The thermodynamics of long-duration spaceflight also influences the design of habitats. artificial gravity, if provided through rotation, would create temperature gradients and airflow patterns different from those in microgravity. Engineers must consider how heat rises or spreads in such environments, ensuring that ventilation and cooling remain effective. Radiation shielding, which we discussed earlier, interacts with thermal management as well. Dense materials used for shielding can retain heat, affecting temperature control. Water, sometimes proposed as part of radiation shielding, has high thermal capacity and can help stabilize temperatures, but it must be integrated carefully into the overall design. All of these factors illustrate that sustaining life over decades is not simply a matter of carrying supplies. It is a matter of maintaining dynamic systems in balance, constantly managing energy flows and material cycles in accordance with the laws of thermodynamics. There is also a psychological dimension to this balance. Living in an environment where every resource is recycled and every system must function reliably can shape how people think about consumption and waste. Habits that seem trivial on Earth, such as discarding unused materials or leaving lights on unnecessarily, would take on new significance in a closed system where efficiency is essential. Over time, the crew might develop a culture of careful stewardship, where maintaining balance becomes part of daily life. This cultural adaptation could be as important as any technological system in ensuring the success of a long-duration mission. The longer the journey, the more thermodynamics asserts itself. Systems drift, materials age, and entropy steadily increases. Continuous maintenance, monitoring, and adaptation become not occasional tasks, but the routine fabric of life aboard the spacecraft. Designing for such conditions requires a different mindset than designing for short missions. Instead of optimizing for peak performance over a few days or months, engineers must optimize for stability and resilience over decades. Simplicity, reliability, and ease of repair become more valuable than maximum efficiency or speed. This perspective also reinforces the practicality of one-way missions. Every additional year of operation increases the demands on life support systems, power generation, and maintenance. A return journey doubles the required duration, compounding the challenges of sustaining a stable environment. For early interstellar missions, it may be far more feasible to design spacecraft that operate reliably for a few decades, rather than attempting to guarantee flawless operation for a century or more. Settling at the destination reduces the need to maintain propulsion systems and other components required for the return trip, allowing resources to be focused on long-term habitation instead. As these considerations come together, it becomes clear that thermodynamics is not merely one aspect of interstellar travel. It is the underlying framework that governs every process aboard a spacecraft, from the flow of electricity to the recycling of air and water, from the durability of materials to the comfort of the crew. And once the realities of energy, entropy, and long-term stability are fully understood, the broader picture of interstellar travel begins to take shape in a different way. The journey outward is not only a technical challenge, but also a commitment, a decision to build systems and communities that can endure far from their point of origin, guided by the quiet but unyielding laws that govern energy and time. If you step back for a moment and look at the whole picture we've been exploring, the conclusion does not arrive suddenly. It appears gradually, almost quietly, as each piece of physics settles into place. Distance, energy, propulsion, radiation, heat, time dilation, communication delays, life support systems, and the steady influence of entropy all point in the same direction. None of these factors alone absolutely forbids a return journey to another star, but taken together, they shape the reality of what such a journey would mean, and why the first voyages outward will almost certainly be one way. At its heart, the reason is simple. The universe is vast, and motion through it requires energy. The faster you move, the more energy you need. The farther you travel, the longer your systems must function without resupply. And the more energy you must carry, the heavier your spacecraft becomes, which in turn demands still more energy to accelerate and decelerate. This chain of cause and effect is not a technological limitation that might vanish with better engineering. It follows directly from the basic laws of physics. Distance is the first and most obvious part of the story. The nearest star lies more than 4 light-years away, a distance so large that even light itself needs years to cross it. Any spacecraft must travel more slowly than light, which means travel times measured in decades at best and far longer at more moderate speeds. Those decades are not empty stretches of time. They are filled with continuous demands on life support systems, power generation, shielding, and maintenance. Energy is the second piece, and it is the one that quietly dominates every calculation. Accelerating a spacecraft to relativistic speeds requires enormous amounts of energy. Slowing down requires nearly as much again. If a return trip is planned, the process must be repeated, doubling or even tripling the total energy budget. Carrying enough fuel to accomplish all of this quickly becomes impractical, even with advanced propulsion methods. The rocket equation expresses this reality in mathematical form, but its meaning can be understood without equations. Every kilogram of fuel needed later in the journey must be accelerated at the beginning. That extra mass demands extra energy, which requires more fuel, which adds more mass, and so the cycle continues. Eventually the spacecraft becomes mostly fuel, with very little room left for the people or equipment it was meant to carry. This is why so many serious proposals for interstellar missions rely on methods that reduce the amount of fuel on board, such as beamed propulsion or sails. Yet these methods introduce new challenges, particularly when it comes to slowing down at the destination. Accelerating outward may be possible with energy supplied from afar, but decelerating requires energy or momentum exchange at the far end of the journey, where no infrastructure yet exists. Even if propulsion and deceleration are solved, other constraints remain. Interstellar space is not perfectly empty. Radiation and dust pose hazards that grow more serious as speed increases. Shielding against these hazards adds mass, which increases energy requirements. Heat generated by impacts, onboard systems, and radiation must be managed continuously, and in the vacuum of space, heat can leave only by radiation, a slow and carefully balanced process. Thermodynamics, often invisible in everyday life, becomes a central concern over decades of travel. Air, water, and nutrients must be recycled with extraordinary efficiency. Machines must operate reliably for years without replacement. Materials age, components wear, and entropy steadily increases, requiring constant maintenance and repair. Designing systems that can endure for the duration of a round trip, perhaps lasting a century or more, is far more difficult than designing systems for a one-way voyage of shorter duration. Time itself adds another layer to the story. Relativistic effects mean that travellers moving at high speed experience time differently from those who remain on Earth. A journey that feels like a few decades to the crew might span a longer period on Earth. Even if a return were physically possible, the travellers would come back to a world that had moved on without them, changed by years or generations of history. Communication delays reinforce this separation. Messages between stars take years to travel, making real-time contact impossible. A spacecraft becomes an independent community, making its own decisions and solving its own problems. Over time, the cultural and emotional distance between travellers and those who remain behind would grow, adding a human dimension to the physical separation. Gravity and orbital mechanics shape the final stages of the journey. Arriving at another star requires shedding enormous kinetic energy and entering stable orbits. Each maneuver demands precision and resources. Planning for a return journey would require repeating these steps in reverse, doubling the demands on propulsion, reliability, and energy. When all of these factors are considered together, the idea of a one-way mission begins to look less like a limitation and more like a practical starting point. By eliminating the need to carry fuel for the return trip, and by reducing the required operational lifetime of propulsion systems, engineers can focus on making the outward journey and long-term survival at the destination as reliable as possible. This does not mean that return journeys will never happen. Over centuries or millennia, as technology advances and infrastructure spreads from one star system to another, travel between stars may become more flexible. Refueling stations, relay points, or entirely new propulsion methods could change what is possible, but the first journeys, the ones that cross the Gulf for the first time, will almost certainly be undertaken with the understanding that home lies behind, not ahead. There is something profound in that realization, though it is not dramatic in the way that stories sometimes portray it. It is simply the quiet acknowledgement that physics sets the stage on which exploration unfolds. The laws of motion, energy, and time do not forbid us from reaching the stars, but they shape the way we must do it. And yet, knowing all of this, the idea of travelling to another star does not lose its power. In some ways, it becomes even more meaningful. A one-way journey is not merely a trip. It is a commitment, a decision to build a new chapter of human history in a place that no human has ever seen directly. Throughout history, people have made similar journeys on smaller scales. Groups crossed oceans in fragile ships, carrying everything they needed, knowing they might never see their homeland again. They were guided not only by necessity but by curiosity, by the desire to see what lay beyond the horizon. The horizon has changed, but the impulse remains familiar. The stars are no longer just distant lights. They are destinations, each one surrounded by its own worlds, its own possibilities, waiting in silence. If the first travellers set out, they will do so with a clear understanding of what the journey means. They will know that returning is unlikely, that communication with Earth will be slow, and that their lives will unfold far from the place where humanity began. And still, they may choose to go, because exploration has never been only about returning. It has also been about extending the reach of life, about learning, about discovering what exists beyond the limits of the known world. The physics that makes the first journey one way does not diminish that purpose. It simply defines the terms under which it must be pursued. So as you think about this, perhaps lying comfortably, listening in the quiet, it can be interesting to imagine what such a journey would feel like. Not in a dramatic or hurried way, but slowly, patiently, the way time itself unfolds in deep space. Years passing, systems humming softly, stars shifting almost imperceptibly against the darkness, and the destination growing brighter little by little. Somewhere far ahead, a new sun rising not over a familiar horizon, but over a world that has never known human footsteps. And back here, on Earth, the night sky would still be filled with stars, most of them unchanged to the naked eye. One of them holding a small, distant world where travellers from another time had begun to build a life beneath an unfamiliar sky. The universe would remain vast and quiet, governed by the same steady laws, while human stories continue to unfold within it, slowly, patiently, one journey at a time.